Greetings everyone! Welcome back to General Chemistry. Today we're going to be continuing where we left off last time. Today we're going to do more acid and base equilibrium stuff, and we'll also look at solubility and precipitation in more detail. Now that we know about equilibrium, things that we referred to in the past as being insoluble are not so insoluble anymore. Let's begin. So I kind of hinted at this in the previous video. I did say that we were going to start off the next video, which is now this video, with the common ion effect. So what is the common ion effect? Let's write out an example to try and illustrate this. Let's illustrate it with the numbers and then try to explain it in a more general mathematical sense. Let's say I have acetic acid. Let's say I have acetic acid, so that's going to be C2H3O2 is one way of writing it. And let's say I put it in some water, of course, and it dissociates, giving us the acetate ion and hydronium ion. Okay, and let's say I do this process twice. Let's say I do this in two different beakers. And one of the beakers is just pure water. And I add, let's say, well, I'll figure out how much I add later. And over here, instead of pure water, let's say that it's let's do 0.010 molar hydrochloric acid, which is one of our strong acids. And let's say in each of these I put in the same amount of acetic acid. Let's say I put in enough acetic acid to make the starting concentration of acetic acid. Let's go with 0.10 molar. 0.10 molar of acetic acid. Okay. Maybe I shouldn't have used HCl. Actually, no, it'll be fine. We'll make a comparison based on the percent dissociation. What's the percent dissociation of your acetic acid in both cases? Let's go ahead and calculate that. So in the first case, we know how to deal with that. We've seen this enough times in the previous video. We take the dissociation constant of acetic acid, which I happen to know is 1.8 times 10 to the negative 5. It's just one of those classic examples that is so commonly used that eventually, without even trying, you start to memorize the number. And we set that equal to the, let's see, if you were to set up your ice table, you would end up with x squared over c minus x. I would hope that you've practiced enough examples that you already recognize this by this point and you don't actually need to set up an ice table for it. But yeah, if you can't see immediately why it's going to be x squared over c minus x, you may want to go back to the previous video or even the previous two videos and do some review. So yeah, that'll be the case for this one. And of course, the x is going to be negligible, so this is just going to reduce to x squared over c. For the other beaker, well, the presence of HCl means there's already a starting concentration of the hydronium. The presence of HCl means that we already have a starting concentration of hydronium. for every 1 molar of HCl, we get 1 molar of hydronium and 1 molar of chloride, but the chloride ion doesn't do anything here, so we'll ignore it. So if I were to list off the numbers, starting concentration for acetic acid in the second beaker is 0.10 molar, and will decrease by X. Starting concentration of acetate ion is going to be 0 and increase by X. Starting concentration of hydronium is going to be 0.010 molar and increase by X. Okay, so for the second beaker's case, we're going to get Ka, which is still 1.8 times 10 to the negative 5, equals X times 0.010 plus X. Over C minus X. All right. So for this first case, I'm going to assume the X is negligible, giving us X squared over C equals 1.8 times 10 to the negative 5, C being 0.10 molar. So if I go ahead and write that out, we get 1.8 times 10 to the negative 5 equals X squared over 0.10. If I multiply the 0.10 to the left-hand side and take the square root, what do we get? Let's see, times 0.10, take the square root, and I'm getting X is 1.34, well, 1.3 times 10 to the negative 3. Is that negligible in comparison to 0.10? Yes, it is, because 1.3 times 10 to the negative 3 is 0.001. So it would be at the third decimal place. If you did subtract it out, you'd still round back up to 0.10 anyway. Okay, so in this case, we get X equals 1.3 times 10 to the negative 3. And so our percent dissociation, that's going to be X over C times 100%, 1.3 times 10 to the negative 3, divided by 0.10 times 100%. That's 1.3%. 1.3% dissociation. Okay. So that's the beaker on the left where you put it in pure water. What about the beaker on the right? So for the beaker on the right, X is going to turn out to be much smaller. And I guess much is a relative concept, so I should probably just say smaller. If we assume X is negligible in comparison to C, then we would end up with 1.8 times 10 to the negative 5 equals X times, I'm also going to go ahead and assume that X is negligible in comparison to the 0.010 from the initial concentration of the hydronium ion. I'm going to go ahead and assume that 0.010 plus X is just 0.010. Over C, which is 0.10. Okay, maybe I should have chosen different numbers than just ones to avoid confusion. Okay, if I go ahead and work this out, then multiply by 0.10 and divide by 0.010, and we get, let's see, wait, I can do this without a calculator. Multiplying by 0.1, that makes it 10 to the negative 6. Dividing by 0.01, that makes it 1.8 times 10 to the negative 4. 1.8 times 10 to the negative 4. And I guess I forgot my units. It's in units of molarity. Okay, is that indeed negligible? It's definitely negligible in comparison to C because it's a smaller value than what we got for the pure water beaker. Is it negligible in comparison to 0.010? 0.010 plus 1.8 times 10 to the negative 4 is going to be 0.01018, and that's just going to round to 3 decimal places anyway, so yes, our assumption that it's negligible in comparison to 0.010 was valid. Okay, then the percent dissociation in this case is 1.8 times, whoops, what am I doing with my calculator? 1.8 times 10 to the negative 4 divided by the starting concentration, which was 0.10, times 100%, and that gives me 0.18% dissociation. 0.18% dissociation. So a little more than a tenth of the dissociation of the beaker on the left, of the sample on the left. Okay, so when there's already hydronium present in the solution, you end up with less dissociation overall, even if you keep all other things equal. This still would have worked if instead of hydrochloric acid, if I had sodium acetate, in which the sodium will just be a spectator ion and the acetate ion will just, float around in the solution. In that case, we would still end up with the same result. It would just be that the hydronium starts at 0 and increases by x, while the acetate starts at 0.010 and increases by x. You'd end up with the same things on the numerator and the same things in the denominator, so you'd get the same x, you would get the same percent dissociation. So it doesn't matter which of the product ions is already present in the beaker. If either of these ions is present, or both, then it's the same effect. There's a reduction in the extent to which this dissociation goes forward. All right, so to prove mathematically that this is a general trend, let's go ahead and write, I guess we can go with Ka, but it's the same thing if it was a Kb. If you have Ka for some generic reaction, some generic dissociation of an acid, Ha plus H2O in equilibrium with A minus plus H3O plus, then you're going to get Ka equals final concentration of the conjugate base times final concentration of hydronium over final concentration of the acid. So if I rearrange this for one or the other, it doesn't really matter. If I rearrange for either one of these, so I can either say that the hydronium concentration equals, let's see, multiply by HA and divide by A minus, so it's going to be Ka times HA over A minus, and if I did it with the A minus and the H3O plus reversed, that's also a calculation you can do. So Ka times HA over hydronium. So that covers both cases. If you're trying to add this weak acid to a solution that already contains the conjugate base, then the amount of hydronium you would get is proportional to the dissociation constant and the amount of weak acid you add. That's not news to us, at least it shouldn't be. And inversely proportional to the amount of conjugate base. And if you already have some of it to begin with, then this denominator increases, which lowers the amount of hydronium generated. And of course, if hydronium is already in the solution, then you just apply the same logic to this equation. The amount of conjugate base generated will be inversely proportional to the amount of hydronium that's in there. So if you already have a lot in there to begin with, this is going to be a high number, which lowers this overall value. So yeah, this is what's known as the common ion effect. And the reason it's called the common ion effect is because the solution that exhibits the common ion effect, in this case it had, I guess it had hydrochloric acid in it, but it can also have sodium acetate or something like that. If the solution that you're adding your weak acid or weak base to already contains ions that it has in common with the equilibrium of your weak acid or base, in this case the common ions being either acetate or hydronium, then you will see the common ion effect take place. Really, it's kind of like Le Chatelier in a way. If you already have a lot of product, then the equilibrium isn't going to go as far to the right. It's still going to need to go at least a little bit to the right to establish equilibrium, but it already has a head start, is what I'm saying. Okay, so that's the common ion effect. It also works for weak bases, even though we used weak acids in our example. That shouldn't come across as a surprise to you. So let's have a look. We can take advantage of this common ion effect in order to create a very special type of solution that's known as a buffered solution. So let's talk about that. Let's talk about a buffered solution. Buffered solutions, also known as buffers. So normally when you try to add a strong acid or a strong base to a solution, let's say you add it to pure water, for example, or actually no, let's say we have a solution, let's say we've got an HCl solution, so we've got hydrochloric acid in here, and let's say the pH is equal to, let's see, if it's acidic, so it's going to be below 7. So let's say pH is equal to 3.00, for example. So that means that we have a hydronium concentration equal to 1.0 times 10 to the negative 3 molar, or 1 millimolar if you prefer. And what happens if I add some sodium hydroxide to it? What happens if I come in here and add a strong base, add something like sodium hydroxide in there, and let's say we add enough sodium hydroxide that it's equivalent to, I don't know, let's keep it simple, 0.10 molar worth of sodium hydroxide. What happens to the pH now? Well, let's see. So sodium hydroxide is going to react with the hydronium that's already present in the solution. And since it's a strong base, no equilibrium arrows, it just goes straight to the right. And of course, let's see, so the hydronium with the hydroxide is going to give you 2 waters. Well, hold on. No. Because it depends on how much we have. No, it's not going to give you 2 waters. It's going to give you some water and some leftover hydroxide. Okay, well, I guess, fine. 2 waters plus, I guess, the sodium ion on its own. I'm overthinking this way too much. Okay, so we've got 1.0 times 10 to the negative 3 molar of hydronium. We've got 0.10 molar of sodium hydroxide, which means that we're going to run out of hydronium first. Hydronium is our limiting reactant, so this is going to decrease by 1.0 times 10 to the negative 3 molar. The sodium hydroxide is going to decrease by 1.0 times 10 to the negative 3 molar. And I guess the water will increase by whatever the equivalent of this is. We don't care. The water doesn't really affect the equilibrium. And the sodium ion, we also don't really care. It's a spectator ion. So then we have leftover sodium hydroxide. How much of it do we have? Well, 0.10 minus 0.0010 is going to be 0.999, which rounded to 2 decimal places is still... Wait, did I say 0.099, which rounded to 2 decimal places is still 0.10. So effectively, your sodium hydroxide leftover is still 0.10 molar, and it's going to dissociate on its own in the water and just form more sodium ion plus hydroxide ion. It'll give you 0.10 molar worth of both. It'll give you 0.10 molar of both. We don't really care about the sodium ion since it's a spectator. It's not going to do anything relevant to us. But this is relevant. We now have approximately 0.10 molar of hydroxide ion in the solution, and we've gotten rid of all the hydronium. So now the pH has become pH equals, what's the new concentration of hydronium then? I mean, we didn't really eliminate it all because of the self-ionization of water. There will still be trace amounts of it. Let's see. So if we assume this is at room temperature, 1.0 times 10 to the negative 14 divided by 0.10 gives us, gives us a hydronium concentration of 1.0 times 10 to the negative 13, which gives us a pH of 13.00. So the pH was 3, it shot all the way up to 13.00 just by adding 0.10 molar worth of sodium hydroxide. So yeah, pH can change very, very drastically. But buffered solutions have the ability to resist this effect. Buffered solutions have the ability to resist drastic changes in pH. Of course, there are limitations on how effective this can be, but let me show you a visual before we move on. So right there in front of you, you see 2 solutions. One of them is unbuffered, and the other one is buffered at a pH of 8.0. Both of them appear to be yellow at the current moment. Before you add some, what did they add? They added hydrochloric acid. I'm guessing this might be methyl red or methyl orange for the indicator that they're using. Does it say in the caption anywhere? Yeah, it's methyl orange. Okay. And they add some hydrochloric acid, 0.01 molar worth of it, a tiny amount in terms of concentration. The buffered solution, as you can see in the image on the right, is unaffected, while the unbuffered solution, its pH drastically changed. In this case, I guess its pH went down because you were adding a strong acid, and you witnessed a color change. It brought the pH down significantly enough that you passed the point where methyl orange will have its color change. So how do these buffer things work? Well, they take advantage of the common ion effect. So what they will tell you in class is that the recipe for making a buffer is combining an acid, a weak acid, with a salt of its conjugate base, or a weak base with a salt of its conjugate acid. So the basic buffer recipe is a weak acid plus salt of its conjugate base or weak base plus a salt of the conjugate acid of its conjugate. So, for example, if I have a solution in which I mix acetic acid with a salt of its conjugate. The conjugate of acetic acid is the acetate ion, and a salt of that, for example, is sodium acetate, or potassium acetate, or rubidium acetate. The spectator ion doesn't really matter. It's the acetate ion that we want. I mean, I guess it kind of matters because it has to be soluble. It's not going to be good news if it's not soluble. So, silver acetate is soluble. Oh well, if you can think of some insoluble acetate, that wouldn't be a good salt to use. Okay, an example of a weak base and a salt of its conjugate. So, for example, ammonia and a salt of its conjugate. The conjugate of ammonia is the ammonium ion, NH4+. So we're going to need some negative counter ion to keep the charge balanced. Chloride ion works, bromide, iodide, those are all fine. Let's say bromide. Fluoride would not be a good choice because the fluoride ion is itself a weak base, and that'll interfere with things. You want the counter ion to be something that doesn't affect the equilibrium. So yeah, that's the basic recipe for a buffer, but there is another way to make a buffer. Instead, if you don't have a salt of the conjugate, then you can just make it by adding a strong acid or strong base. If I have a weak acid, I can add some strong base to it, not a whole lot, just enough to neutralize some of the weak acid, so there will still be some left over, but some will also be converted into the conjugate base. Similarly, if you have a weak base, just react it with some strong acid in order to make some of its conjugate base. Let's do a weak base example to illustrate this. Let's do it with ammonia, actually. So let's say I react, 0.10 molars worth of ammonia with hydrochloric acid. And let's say that I have, let's make 0.03. Yeah, let's add 0.030 molar worth of hydrochloric acid. Not enough to neutralize all of the ammonia, but enough to generate some ammonium ion. Then this would give us some ammonium ion, of course, plus your spectator ion, which in this case is chloride. Or you could just write it as one thing, as ammonium chloride if you want. And yeah, so this starts at 0.10 and decreases by 0.030. Whoops, that's not how you write that. I guess I'll write it up here, minus 0.030. And this is just going to decrease all the way. It's going to run out. And this is going to start at 0 and increase by 0.030. And same thing for the chloride, but we don't care about the chloride. Okay, so in the end, what you're left with is 0.10 minus 0.030 is 0.07 molar of ammonia, and no HCl, and 0.030 molar of ammonium. So there you go. You've got the weak base and its conjugate both present in significant amounts. What counts as significant is, if the numbers are close enough to each other. It doesn't have to be a 50-50 mix. In fact, I think even a 99-to-1 ratio still works for making a buffer. But the best buffers are usually going to be close to 50-50. Usually it's a better buffer if you can get the mix as close to 50-50 as you can. But you can have a pretty big ratio between the base and its conjugate, or the acid and its conjugate, and still be in the buffer zone, so to speak. Okay, so yeah, you can make buffers by mixing a weak acid and a salt, or a weak base and a salt, or a weak acid with some, but not too much, strong base, or a weak base with some, but not too much, strong acid. Now then, I said buffers take advantage of the common ion effect. How is that so? Let's carry on with our example of ammonia, and I'm going to add a 0 here so that I can get another 0 over here, because I'd like to have at least 2 sig figs. And let's have a look at the sort of equilibrium that can be established in this buffer. So you've got ammonia is now floating in a solution that has other ions, of course, I guess chloride ions, and it can interact with the water. To form ammonium ions and hydroxide ions. Similarly, the ammonium ion that we have is in there, and it can interact with the water to generate ammonia and hydronium ions. Neither of these processes will proceed very far to the right. Neither process is going to make much progress. And that's because of the common ion effect. I have 0.070 molar of this stuff, which is not a whole lot, and then I've got 0.030 molar of ammonium, having some ammonium already present, having some product already present, is going to significantly reduce the amount of dissociation that can occur. You're not going to generate a whole lot of hydroxide from this. Same story over here if you reverse, well, not reverse it, but if you look at the dissociation of ammonium ion, same idea. If you want ammonium to dissociate, there's already some ammonia present in the solution, so the dissociation of ammonium can't progress that much. And there's your, well, I wouldn't really call it a dilemma because it's actually very useful. But yeah, there's your situation. Neither of these processes can proceed very far. So let's go ahead and put together an equation to calculate what would the pH of such a solution be. I will just focus on the ammonium part of it. I'll just focus on this second one. It shouldn't really matter which one we pick because the amount of hydronium we calculate for this should agree with the amount of hydroxide we would calculate using this process. So it shouldn't really matter which one we use to calculate the pH. If we used the one on top, we could, I guess, get the pOH and subtract it from 14, or use Kw over the final concentration of OH minus. We've been through that in the previous video. You should know how to do it by now. So, let's see. The equilibrium constant for this process, Kb, or no, that's an acid. Ka is equal to 5.6 times 10 to the negative 10 times 10 to the negative 10. So let me go ahead and write out 5.6 times 10 to the negative 10 is going to be equal to, this is going to decrease by x, this is going to increase by x, and this is just going to be x. It starts at 0 and increases by x. So that's going to be 0.070 plus x for ammonia times x for hydronium over 0.030 minus x. We've got common ion effect going on here, so it's pretty reasonable to expect that x will be very tiny. 0.030 minus x is probably still going to be 0.030 after rounding. Same goes for 0.070 plus x. I'm going to assume that this approximately equals 0.070 times x over 0.030. Okay, 0.030 times 5.6 times 10 to the negative 10 times 0.030 is 1.68 times 10 to the negative 11. I'm going to round that to 1.7 times 10 to the negative 11. And then we need to divide that by 0.070. And that gives me about 2.4 times 10 to the negative 10. X equals 2.4 times 10 to the negative 10 molar. So that's our concentration of hydronium. So it looks like our pH is going to be the negative log of that. I should state that that equals our hydronium concentration. pH is going to be the negative log of that. Negative log of 2.4 times 10 to the negative 10 is about 9.62. 2 sig figs, 2 decimal places. 9.62 is the pH of this buffered solution. Now, here comes the interesting part. here comes the interesting part. What if I now take this buffer and I add either a strong acid or a strong base? Let's add a strong base, for example. Of course, I don't want to add too much, but let's say I add let's say I add 0.0, let's add 0.010 molar. Let's suppose I add 0.010 molars worth of sodium hydroxide. Maybe I should change it up and make it potassium hydroxide, but you know, sodium hydroxide is the first base that comes to mind for me, and the first acid that comes to mind for me is hydrochloric acid, sometimes nitric acid. I'll try to change it up when we have another opportunity, but I won't make any promises. If I add 0.010 molar sodium hydroxide, what is that going to do? Let's see its effect on the starting conditions and then recalculate the X value using equilibrium concepts. If I add 0.010 molar sodium hydroxide, then that's going to convert 0.010 molar worth of ammonium ion into ammonia and produce some water, which we don't care about. So if I put sodium hydroxide with the ammonium ion, then that's going to produce some ammonia and some water. If I added acid, then the acid would have reacted with the ammonia to produce ammonium. But yeah, adding a base would have that effect. So if I've got 0.010 molar here, and my ammonium was 0.030, and my ammonia was 0.070 molar, and water I don't care, this is going to decrease by 0.010, this is going to decrease by 0.010, and this is going to increase by 0.010. We're going to get rid of all the sodium hydroxide. It's the limiting reactant. We have to run it out since it's a single arrow, not a double arrow. And we're left with 0.020 molar of ammonium ion and 0.080 molar of ammonia. Recalculate in terms of equilibrium what the pH is going to be. So we've got 5.6 times 10 to the negative 10 is going to be basically the same equation we have here, just change these two numbers. So I'm going to just make the assumption that the X is still negligible and get 0.080 times X over 0.020. Okay. If I go ahead and calculate my hydronium concentration, that's going to be 5.6 times 10 to the negative 10 times 0.020 is about 1.1 times 10 to the negative 11. And then divide that by 0.080, and that's about 1.4 times 10 to the negative 10. So that's your hydronium concentration, and if we take the negative log of that, you will find that it's still somewhere between 9 and 10. negative log of 1.4 times 10 to the negative 10 is 9.85. 9.85. Oh, wait, what am I doing? No. pH equals 9.85. There we go. So the pH didn't increase all that much this time. Compare that with what we did earlier when we added, I think it was, wait, was it the same amount? No, it was 10 times the amount of sodium hydroxide. When you added 0.10 molar sodium hydroxide, the pH shot up from 3 to 13 in an unbuffered solution. But in the buffered solution, it's not just because it's a tenth of the amount. It's not just because it's a tenth of the concentration. In fact, if I recalculate real quick, if I change this to 0.010, then what effect will that have? So 1.0 times 10 to the negative 3. Well, I guess that would... So if it was 0.010, then we'd be left with 0.009 over here. So you'd be left with 0.009. Is that right? No, wait. If I had 0.010 molar worth of sodium hydroxide and I subtract 1 times 10 to the negative 3 from it, yeah, that's 0.009. Okay, so 0.009 would dissociate and give us 0.009 molar of hydroxide. And then if I do kW 1.0 times 10 to the negative 14 divided by 0.009, that's 1.1 times 10 to the negative 12, or I guess just 1 times 10 to the negative 12 because of sig figs. And the negative log of that is 12. So even if I used a tenth of the sodium hydroxide in this example, I would have gotten a pH of 12. So it's not because of the concentration of sodium hydroxide used being 10 times smaller than the unbuffered example. It's because of the common ion effect. It's because of the common ion effect. We have enough base in the solution to cushion the blow whenever you add a strong acid, and we have enough acid in the solution to cushion the blow whenever you add a strong base in order to retain this sort of balance. Of course, I could totally break this by just dumping in a ton of sodium hydroxide. If I used 0.1 molar sodium hydroxide, then it would be the excess reactant, and at that point it would be over. At that point, it's not operating as a buffer anymore. You've practically neutralized any ammonium that was in there, and you'll have excess hydroxide ions, which will raise the pH dramatically. But yeah, the common ion effect, so long as you don't add too much sodium hydroxide, well, too much strong base or strong acid, then buffered solutions tend to stay very close to their original pH. So, there is an equation that can help us save time instead of having to go through this whole process each and every time. There is an equation that we can derive that will simplify things. So, let's see. Let's just write the equilibrium for a generic acid again. HA plus water. It doesn't have to be an acid. You could do this with a base too, but I'll just go for the acid. And if you want to do it for the base as additional practice, you're more than welcome to do so. I don't think they'll ask you to do this derivation, but, you know, it It couldn't hurt. HA plus H2O gives us A minus plus hydronium. Okay, let's see. So we've got those, and so I would say that Ka in general would be equal to the concentration of A minus times the concentration of hydronium over concentration of HA. And if I solve this for the concentration of hydronium, then concentration of hydronium equals, let's see, it's Ka times HA and divided by A minus. Ka times HA over A minus. All right, and if I want to calculate the pH, then I just take the negative log of this. pH equals negative log of hydronium equals negative log of Ka times HA over A minus. Taking advantage of the logarithm rules, I can say then that pH equals, I'll keep the negative on the outside, the log of a product is the sum of the logs. So I can say that's log of Ka plus log of HA over A minus. Okay, and if I distribute the negative sign, then that's going to be negative log of Ka minus log of HA over A minus. Now, negative log of H is called pH, and I guess hydronium also still counts as H. Negative log of OH minus is called POH. So negative log of Ka, that can be called pKa. So in general, the lowercase p just means negative log of. So pH equals pKa, and then for minus log of HA over A minus. So what I'm going to do is I'm going to move the negative 1 into the log using the power rule of logarithms. So that'll make it plus log of all this stuff raised to the negative 1. It's going to be log of HA over A minus, all raised to the negative 1 power. Let me draw a dividing line between those. And ultimately we end up with pH equals pKa plus log of, it's going to become A minus over HA. If you raise it to the negative 1 power, that's just the reciprocal. Usually this is written in more general terms. Usually it's written as pH equals pKa plus log, what is A minus? It's the conjugate base. So we say log of base over HA, which was the acid, plus log of base over acid. And this is what's known as the Henderson-Hasselbalch equation. Or as one of my students called it many years ago, the David Hasselhoff equation. Not that David Hasselhoff has anything to do with it, but that's just what it sounded like to her. The Henderson-Hasselbalch equation. Of course, you could derive something similar to this. You could derive that POH equals PKB plus log of acid over base. You can certainly do this, but you don't need this. If you need the POH, you can calculate the pH and then use pH plus POH equals, PKW. pH plus POH equals PKW. PKW is usually 14 if it's at room temperature, but if it's not at room temperature, you know what to do. We discussed it in the previous video. So yeah, so long as you have this relationship, you don't need a specific equation for POH. So we don't really need this, but if you want to derive it on your own, I think that might be a worthwhile exercise. But yeah, the Henderson-Hasselbalch equation. Now, note that the Henderson-Hasselbalch equation is an approximation. Note that it is an approximation. We base it on the idea that we'll have the common ion effect. What's the word I'm looking for? It's based on the idea that we're going to have a strong common ion effect, and that's not always going to be the case. It's only going to be a significant common ion effect if we've got a really good conjugate acid-base ratio. If the ratio is too drastically in favor of the base or the conjugate acid, then Henderson-Hasselbalch starts giving you worse and worse approximations of the pH, and at that point you're better off just going back to traditional methods, and you'll probably have to solve some quadratic equations to figure out the equilibrium and whatnot. So Henderson-Hasselbalch is an approximation. Generally, the further the pH is from pKa, the worse your approximation is getting. But yeah, your pH is going to be some starting point, whatever the pKa value is, and then you can add or subtract from that by increasing or decreasing the acid-base ratio, and the way you do that is by either adding some strong base or adding some strong acid, whatever you are trying to do. If you want to raise the pH, you would add some strong base. That would increase the base to acid ratio, which increases the log of the base to acid ratio, which gives you something positive that you can add to pKa. And of course, if you do the opposite, then you're increasing the acid or decreasing the base, decreases this ratio overall, decreases the log, probably gives you something either not as positive or gives you something negative even that you can subtract from the pKa value to bring the pH down. All right. So, also before I work an example of this, let's talk about volume. Volume usually isn't going to matter when applying the Henderson-Hasselbalch equation. The concentration of base over concentration of acid, that's just going to be, well, it's going to be your moles of base over volume divided by, and I guess I should write it out, concentration of base over concentration of acid equals moles of base over total volume divided by concentration of acid, which is moles of acid over total volume. These are molar concentrations after all. The total volume is going to be the same for both the base and the acid because they're swimming in the same solution. They occupy the same space, so they should have the same volume. So these volume values are going to cancel out. Whatever the volume is, it cancels out anyway. So you don't necessarily have to take the ratio of the concentrations, though you probably should if the concentrations are already given. You can just use the concentration, or not the concentrations, you can just use the ratio of the moles instead. If you know how many moles of your weak base and its conjugate are in your solution, don't waste time trying to divide by the volume and calculate the concentrations. You already have, it's going to be the same ratio. Okay, should we do... Okay, I'll do some examples now, and then we'll talk about best practices for preparing buffers and the idea of buffer capacity and whatnot. Let's take a look at some examples. Explain why a buffer can be prepared from a mixture of ammonium chloride and sodium hydroxide, but not from ammonia and sodium hydroxide. I think that was the exact one that we did, is it not? Was it? No, we did ammonia plus hydrochloric acid to make some ammonium. But we already talked about this. Ammonia with sodium hydroxide, that's not really going to do anything. Sodium hydroxide can react with ammonium to make ammonia, but not the other way around. So that's 77. And if you're wondering why we're starting at problem 77 and not problem 1, these are the remaining problems from the set that we started in the previous video. The way they had the chapters split up wasn't really to my liking, so that's why I decided to cover like 2/3 of a chapter in one video, and then in this video we've got the remaining third plus the next chapter, which is a shorter one. Anyway, 78, explain why the pH does not change significantly when a small amount of an acid or a base is added to a solution that contains equal amounts of... Okay, we've just finished explaining that. It's the common ion effect. That's what buffers do. Okay, 79. Pretty much the same thing. 80. What is hydronium concentration in a solution of 0.25 molar? That's another way of writing acetic acid, and 0.03 molar sodium acetate. Okay, so really simple. Just apply the Henderson-Hasselbalch equation. It's really quick and easy. Don't bother doing equilibrium not concentrations. Don't bother using or trying to calculate the equilibrium concentrations using ice tables is what I'm trying to say. Just go straight for the Henderson-Hasselbalch equation. So pH equals negative log of Ka, which they gave us as 1.8 times 10 to the negative 5, plus log of the base over the acid. So in this case they gave us concentrations. They said the base, which comes from sodium acetate, is 0.030 molar over the acid, which was 0.25 molar. Wait, is that right? Yeah, 0.25 molar. Okay. Units of molarity cancel out. And yeah, let's take a look at what that gives us. Negative log of 1.8 times 10 to the negative 5 is about 4.74, and then log of 0.030 over 0.25, that's going to be 2 sig figs. So when we take its log, we're going to get 2 decimal places. And it looks like that's negative 0.92. So we've got 4.74 for our pKa plus negative 0.92, which gives us a pH of 3.82. And now we can use this to calculate the hydronium and hydroxide concentrations. Hydronium concentration is going to be 10 to the negative 3.82, something times 10 to the negative 4. I mean, I don't think we really need to see the rest of this, but it's a quick calculation. 1.5 times 10 to the negative 4. 2 decimal places in the exponent means we get 2 sig figs. 1.5 times 10 to the negative 4. And if you wanted hydroxide or POH, you know how to do that from what we covered in the previous video. Okay. I'm guessing 81 is going to be similar. Yeah, 81 is similar. 82 is similar. Except you're going to have, be careful about 82. Remember to convert the Kb to Ka of the conjugate acid. Your Henderson-Hasselbalch equation is pH equals pKa plus log base over acid. And also, since it's asking for hydroxide concentration, once you calculate the pH, either convert to the POH and then take 10 to the negative POH, or you can do what we just did with the previous problem and then take Kw over the hydronium concentration. 83, pretty much the same as 82. 84, what is the effect on the concentration of acetic acid, hydronium, acetate ion when the following are added to an acidic buffer solution of equal concentrations of acetic acid and sodium acetate? Oh, well, I guess that's more of a Le Chatelier question than anything else. Yeah, that's just Le Chatelier's principle. You could have done that from 2 videos ago. Well, actually, maybe not, because you didn't know the acid-base stuff 2 videos ago. But you could have done this in the previous video by the end of it. Let's move on to some more problems. Let's see what we've got on this next page. What is the effect on the concentration of ammonia, hydroxide ion, and ammonium ion when the following are added to a basic buffer solution of equal concentrations of ammonia and ammonium nitrate? Nearly no effect, but it depends on how much you add. So potassium iodide, that's not going to have an effect on pH at all. Adding ammonia, that would, well, it would increase the concentration of ammonia, obviously, but so long as you don't add too much, you'll still be in the range where this mixture works as a buffer. Hydroiodic acid, so that's a strong acid. It could lower. Oh, it's not asking for effect on pH. Silly me. I'm jumping to conclusions as I read these. I need to slow down. Okay, so effect on concentration of ammonia, it would decrease if you add hydroiodic acid because you'd be converting some of it into ammonium ion. So ammonium would increase, and if we're increasing the ammonium ion, well, if you're adding acid, then you'll be reducing the amount of hydroxide. No need to overthink it. Part D, sodium hydroxide, opposite of part C. You'll increase ammonia, increase hydroxide, and decrease ammonium concentration. And part E is basically the reverse of part B. Ammonium chloride will increase the ammonium concentration, and since it's a weak acid, it will lower the hydroxide concentration, but not noticeably. Okay, 86. What will be the pH of a buffer solution prepared from 0.2 moles of ammonia and 0.4 moles of ammonium nitrate and just enough water to give 1 liter of solution? The 1 liter doesn't matter. Volume does not matter. I already proved it doesn't. So Henderson-Hasselbalch, just do pKa, which I guess you'd have to look up in a data table. Let's see. Yeah, I'll just write the setup. I'll just show the setup, and you can calculate the number on your own if you really need to know. But pH equals pKa of ammonium ion, since ammonium would be the acid in this case, plus log of base over acid. Our base is ammonia, so we've got 0.20 moles of the stuff over 0.40 moles of ammonium. Moles cancel out, and yeah, the rest is just look up the Ka value or calculate it from the Kb of ammonia if you can't find it in a data table. And there you go. 87. Calculate the pH of a buffer solution prepared from... Okay, so pretty much the same as 86. We'll skip. What about this next page? How much solid sodium acetate trihydrate must be added to 0.3 liters of a 0.50 molar acetic acid solution to give a buffer with a pH of 5. Assume a negligible change in volume as the solid is added. Even if the volume did change, it's not going to matter. We just have to have the correct ratio of the moles of the acid and conjugate base. Okay, let's work through this one, or at the very least show the steps. Show enough steps where I can be confident that you can pick up the rest on your own. Okay, so we have 0.3 liters of 0.50 molar acetic acid. That means that if I multiply it out, 0.3 liters times 0.50 moles per liter is going to be 0.15, yeah, just 0.15 moles, 2 sig figs, right? 0.15 moles of acetic acid. I'll just call it acid for short. And we need a pH of 5. We need pH to be 5.00. So, really simple. Apply the Henderson-Hasselbalch equation. pH equals pKa plus log of, let's see, well, our base is unknown, so I'll just call it moles of base over our moles of acid, which is 0.15 moles. And yeah, figure out your pKa value and then subtract that from 5.00. Okay, let's actually work this out. So the Ka value for acetic acid is 1.8 times 10 to the negative 5 again. So negative log of 1.8 times 10 to the negative 5. I remember it being 4.7 something. 4.74. Okay, so that's 4.74. And if I subtract it from 5.00, then that's 0.26. Oh, I could have done that without a calculator. I feel silly now. 0.26 equals log of moles of base over moles of acid. And since this is log base 10, I would just exponentiate both sides with 10. 10 to the log base 10 cancels out, so 10 to the 0.26 is going to be 1.8. So we get, and I guess I should switch colors here, we get 1.8 equals moles of base over 0.15. Multiply by 0.15, you get the moles of base. And then the question was how much solid sodium acetate trihydrate must be added. So once you've got the moles of that stuff, multiply by the molar mass, and you'll get the amount needed in grams. I trust that at this stage in chemistry that should not pose much of a challenge for you. All right, 89, is that the same? What mass of ammonium chloride must be added to 0.75 liters of 0.1 molar solution to give a buffer with pH of 9.26? Yeah, basically the same thing. 0.75 liters times 0.1 molar gives you the moles of ammonia, and work it out from there. Number 90, a buffer solution is prepared from equal volumes of 0.2 molar acetic acid and 0.6 molar sodium acetate. Use one, okay. What is the pH? Is the solution acidic or basic? What is the pH of a solution that results when 3 milliliters of 0.034 molar HCl is added to 0.2 liters of the original buffer? Okay, let's at least do part C. Well, I guess we'd have to do part A along with it for comparison's sake. Okay. New sheet. So our pH is going to be pKa, which is 4.74 for acetic acid and acetate ion, plus log of, is it 0.2 over 0.6 or 0.6 over 0.2? Acetate is 0.6, that's the base, so 0.6 over 0.200. 3 sig figs means 3 decimal places. It's ultimately going to end up being 2 decimal places anyway, but you know. A log of, well, it's basically 3. Log of 3.00 is 0.477. Positive 0.477. So pH equals 4.74 plus 0.477, which is going to be 5.22 if we round to 2 decimal places. That's a pH of 5.22, which is below 7, so this solution is acidic. Even though there's more base than acid in there, it is acidic. The base just happens to be weaker than its conjugate acid. So much weaker that even at 3 times the concentration, it still doesn't beat out its conjugate acid. Okay, so that's part A, and I guess part B. Part C, what is the pH of a solution that results when 3 milliliters of 0.034 molar hydrochloric acid is added to 0.200 liters of the original buffer? So if you cared about volume, you would make sure to recalculate all the concentrations under the new volume. The new volume being 0.203, because, you know, you're adding the 0.200 liters plus the 3 milliliters, which is 0.003 liters. So there might be cases where you do actually have to do that, so I don't want you to ignore volume entirely, but just learn to recognize the cases where the volume doesn't matter so that you don't waste your time with it. In this case, it's not going to matter what the final volume is. All we care about is the ratio of these guys. This part is set in stone. The pKa doesn't change because the Ka doesn't change. It's a constant. So only thing we care about is the ratio of the base and acid concentrations, which is equal to the ratio of their moles. So 3 milliliters of 0.0, let's see, add 3 milliliters of 0.034 molar HCl. How many moles of HCl is that? How many moles of HCl is that? 3 milliliters is 3/1000ths of a liter, and then 3/1000ths times 0.034, 0.003 times 0.034. So that's going to be 0.00010 moles of HCl. Okay, and we've got, it was 0.2 liters of the original solution, so how much acid and base are already in there? If it's 0.2 molar of the acid, 0.2 times 0.2 liters gives us 0.0400 moles of acid. And for our base, same thing, it's 3 times as much, so that's going to be 0.120 moles of our base. Okay, and adding that much HCl isn't really going to change much. Did I do anything wrong here? It doesn't look like I did. Okay. So the effect of adding hydrochloric acid is that you turn some of the base into its conjugate acid. So you'd subtract 0.00010 moles from your total moles of base and add that to your total moles of acid. So minus 0.00010 and plus 0.00010. Technically, by the sig fig rules, this isn't supposed to change much of anything. But let's ignore the sig fig rules and see if we notice any difference here. So if I calculate pH as 4.74 plus log of base, so what's that going to be? Well, I'll just write out the expression as is, minus 0.00010 over acid 0.0400 plus 0.00010. If I plug all that into my calculator as is, log of 0.120 minus 0.00010 over 0.04 plus 0.00010. Okay, that log is going to be 0.4. Let's see, how many sig figs am I going to have? Well, this would have rounded to 3 decimal places, and this would have rounded to 4, so that's 3 sig figs over 3 sig figs, which is still 3 sig figs. So that's 0.476. So this expression is 0.476, 4.74 plus 0.476. Is that any different from what we had before? I mean, not really. 0.477 and 0.476. Not much of a change. 5.21. Let's see, so that's 1, 2, 3, 4 decimals down. Would have made a difference there, but not so much there. Let me see, if I did log of 0.120 over 0.0401, would I still get? No, that would, oh, actually yes, it would be 0.476. Okay, so we didn't really need to neglect the sig fig rules. You still would have gotten this result if you kept with the sig fig rules. It's just that this top number would have rounded back to 0.120. The bottom number would have only changed by a little bit. Okay, good to know. What else do we have here? Is 91 virtually the same? Looks like it might be. 5.36 gram sample of ammonium chloride was added to 25 milliliters of sodium hydroxide, and the resulting solution diluted to 0.100 liters. What is the pH of this buffer? Is it acidic or basic? And what is the pH that results? 1.3 milliliters of, okay, so same amount of hydrochloric acid as before. Okay, pretty similar, just a different starting setup. So you're going to have to calculate the moles of ammonium chloride from the grams using molar mass. That's not a challenge for you. And then the 25.0 milliliters of sodium hydroxide will convert some of those ammonium chloride moles into ammonia. And from there you'll have your ratio of leftover ammonium and ammonia, and use that to calculate your pH. Part C is not too different from what we did with problem 90. So I think I will leave that one to you. Okay, and I don't think we are ready for this set yet, so let's go back to our document camera and let's talk about Buffer range and buffer capacity. Let's talk about buffer range and buffer capacity. Really, they're just things that you have to understand conceptually. Buffer range and buffer capacity. I guess there might be some definition for these that you can use to actually calculate the buffer range and buffer capacity, but no formulas that you need to know for a general chemistry course or an AP or IB chemistry course, just understanding it conceptually. So the buffer range is basically the range of pH values at which the buffer operates. So if I have, for example, a buffer made with acetic acid, then its buffer range is going to be, it's going to have 4.74 in the middle. The pKa value is going to be somewhere in the middle. And for example, let's say that it works as a buffer from, and I'm just making numbers up here, let's say it operates as a buffer from a pH of 3.10 to 5.38, for example. So it keeps acting as a buffer until you bring the pH so far down that it reaches 3.10 or so far up that it reaches 5.38. Beyond that point, it just ceases to act as a buffer. Again, those are made up numbers, but there is some minimum pH and some maximum pH, and after you cross those lines, you don't have the buffering effect anymore. Buffer capacity. So buffer capacity, let's say I made an acetic acid and sodium acetate buffer, but I prepared it in two different ways. So one of them, and let's say both of them are 50-50 mixtures. So one of them, what I did was I did pH equals pKa plus log of, let's say I mixed 0.10 molar of the acetate ion and 0.10 molar of acetic acid versus another acetate and acetic acid buffer that I made using the same ratio. It's still going to be a 1-to-1 ratio, but I mixed 1 molar of acetate ion with 1 molar of acetic acid. Which of these has the higher buffer capacity? It would be the second one. The second one has 10 times as much acid and 10 times as much base when compared with the first one. So even though they're both going to have the same starting pH, which in this case is just going to be pKa, because when it's 50-50, it's a 1-to-1 ratio, and the log of 1 is 0. So in that case, pH is just equal to pKa, which is 4.74. So even though both of them start at 4.74, if I were to add, for example, 0.05 molar worth of sodium hydroxide, add the equivalent of 0.05 molar of sodium hydroxide. Strong base will forcibly convert your weak acid into its conjugate base, so that basically subtracts 0.05 from your acid and adds 0.05 to the base. So this will become 0.15 over 0.05, while this over here is going to become 1.05 over 0.95. And let's go ahead and calculate the logs of those. So log of 0.15 over 0.05 is about 0.48. I guess I'd round it to 0.5 since it's only going to have one sig fig. Let's not use that color. Let's go with pink. So log of this is going to be about 0.5. Meanwhile, the log of 1.05 over 0.95 is going to be 1.05 over 0.95. That's going to be 2 sig figs, so 2 decimal places, 0.04. 0.04. So the change in pH for the first buffer is 0.5, while the second buffer's pH only changes by 0.04. It's much more capable of cushioning the blow from adding a strong base, or acid for that matter. So yeah, that's the idea of buffer capacity. If you've got higher concentrations but the same ratios, then the buffer with the higher concentrations is going to last longer. It'll work better as a buffer. So those are 2 things that we needed to know about buffers. One more thing to consider: preparation of buffers. So this might be applicable if you are asked to make a buffer with a specific pH in the lab. Preparation of buffers. Let me grab, they don't have a problem for it in the digital textbook, but I do have one in my physical textbook. Let's see. It says you have to prepare a buffer with a pH of 3.50. Desired pH is 3.50. And we have the following 0.10 molar solutions available. 0.10 molar solutions available. So we've got methanoic acid. We've got acetic acid. We've got phosphoric acid. And we've got sodium methanoate, sodium acetate, and sodium dihydrogen phosphate. Sodium methanoate, sodium acetate. Sometimes they write sodium acetate with the sodium at the end in place of the H that gets removed. So if you see that in your book or in your instructor's worksheets or whatever, don't be too weirded out by that. And sodium dihydrogen phosphate. Sodium dihydrogen phosphate. Okay, so those are the solutions that are available to you. And let's see, they didn't really require this, but I'm going to add another requirement. And my requirement is make 1 liter of buffer. Make 1.00 liters of this buffer. So, which combination should I use? Which combination of acid and conjugate base should I use? Well, the best thing you can have is when your pH and pKa are very close to each other. That would be the best choice, because if your pH and pKa are far apart, then that means that the ratio of acid and base here is going to be either very high or very low, depending on whether it's going to be more base than acid or more acid than base. And it's going to be a very, very precise ratio, which is not very practical. It's not going to be easy to get that in the lab. You're going to have to be either extremely careful or use really, really good equipment. It's not worth it. It's better to pick a combination that starts you at a pKa that's close to your desired pH, so that these ratios are not that drastic. They're just going to be easier to work with if you start with something with a pKa close to your desired pH. So let me look up the Ka values for each of those acids. We already know acetic acid, of course. So acetic acid's pKa, yeah, I'll just write the pK, well, I'll write the Ka values, 1.8 times 10 to the negative 5. And then methanoic acid, where is methanoic acid? Oh, I guess they wrote it as formic acid. Okay. So that's 1.8 times 10 to the negative 4. And then phosphoric acid, 7.5 times 10 to the negative 3 for its first dissociation anyway. Its second dissociation is 6.2 times 10 to the negative 8. That's a pretty wide gap, so we don't really have to worry about second dissociation, though that might also come up as a concern if you have to prepare a buffer in the lab. Okay, let's get the pKa values. So if I take the negative logs of these, I already know for acetic acid it's 4.74. For methanoic acid, also known as formic acid, negative log of 1.8 times 10 to the negative 4. I imagine that's just going to be 3.74. Yeah, 3.74. And 7.5 times 10 to the negative 3. Negative log of 7.5 times 10 to the negative 3 is 2.12. 2.12. Okay, so those are your three pKa values, and it looks like we have a very clear winner. A pKa of 3.74 is pretty close to 3.50. So we should use methanoic acid with sodium methanoate, or if you like, formic acid with sodium formate is an alternative name for it. So let's see, we want 3.50 equals pKa is 3.74 plus log of base over acid of, I'll just go with moles of base over moles of acid. So let's see, subtract 3.74, we get negative 0.24. equals log of base over acid. That's not how you spell base. There we go. And 10 to the negative 0.24 equals 10 to the log of that stuff. 10 and log cancel out. And we get 10 to the negative 0.24 is equal to, let's see, that's going to have 2 sig figs, so 0.58. So 0.58 equals the moles of base over the moles of acid. Okay, let's copy this over to another sheet so that we can figure out what volumes we need to use. These are all 0.10 molar solutions, so we need to figure out how much of each we need to use. Even if the solutions weren't equal in molarity, I'm going to show the steps as if we didn't know that they were of equal molarity. So it was 0.58. 0.58 equals moles of base over moles of acid. Multiply moles of acid to the left-hand side, and that becomes moles of base equals 0.58 times moles of acid. Okay, and of course, moles of acid equals molarity of acid times volume of acid, so we can write this as 0.58 times molarity of acid times volume of acid equals moles of base equals molarity of base times volume of base. Okay, and in this case we know what the molarities are. They're each 0.10. So 0.58 times 0.10 is 0.058 times volume of acid equals 0.10 times volume of base. Yes, I could have just canceled them out on both sides, but I'm trying to go through the general process so that it's clear what to do in case MA and MB are unequal. If they were unequal, then I would go and divide by MB, and that would bring us back to 0.58. That might seem pointless for some of you, but I'm sure others appreciate it. All right, so that's one equation and two unknowns. Our other equation is going to be the fact that the volume of the acid plus the volume of the base is going to equal the total volume of the solution, and the desired total volume is 1 liter. All right, so knowing that, I can just make a substitution. Substitute VB with 0.58 VA and plug that into the second equation. So second equation becomes VA plus 0.58 VA. That's 1.58 VA equals 1.00 liters. 1 divided by 1.58 is 0.633. So VA equals 0.633, and the rest must be VB, so VB must be 1 liter minus 0.633. It's going to be let's see, it's going to be 0.37 because it's going to be 2 decimal places, 0.37 liters. or 0.367 if you don't really care about sig figs at this point. But yeah, there you go. So mix 0.633 liters of your acetic acid solution with 0.37 liters of your, or sorry, did I say acetic acid? No, your formic acid. Mix 0.633 liters of your formic acid with 0.37 liters of your sodium formate, and you will have 1 liter of buffer that is at a pH of 3.50. All right, that takes care of that. Now let's talk about how this affects titrations. I guess I still have some room over here. Yeah, let's take a look at titrations. So first I'm going to do the same type of titration that we saw all the way back in video number 4, I believe. I'm specifically talking about acid-base titrations here, not precipitation or redox titrations. So, classic case that we dealt with way back when is titration of a strong acid with a strong base, or a strong base with a strong acid. Strong acid with strong base. So it turns out that if you plot, let's say it's an acid that I have, so I guess I should draw the titration apparatus. So you've got a burette, which has a valve that you can open to let your standard solution, also known as a titrant, start dripping out. It feeds into, usually it's going to be a beaker, though it can also be a flask or some other container that has some unknown, well, not an unknown, but a sample of unknown concentration, some sort of analyte. And you just let your titrant drip in there until you reach some point known as the equivalence point. The equivalence point for acid-base titrations will be indicated by the color change of some sort of acid-base indicator. So we keep letting, I guess let's say we've got a base in here. Let's say we've got a base, a strong base. And over here we've got a strong acid. Strong acid there and strong base there. And we let this continue to drip until we witness a color change, and then we've reached what's called the end point of our titration, which is an approximation of the equivalence point, the point at which the amount of base you've added is equal to the amount of acid that's in your sample, enough to completely neutralize it. So if we were to monitor the pH as we add our strong base drop by drop, let's say on the horizontal axis I plot milliliters of base, and I should probably separate this diagram from the graph. So let's suppose on the horizontal axis I plotted milliliters of base, and on the vertical axis I plotted my pH. Then if I did that, I would get a curve that looks like this. All right, so this is what's known as a titration curve. Titration curve. I guess you don't really need me to spell that out for you, but writing it down might help it stick in memory better. Okay, and of course, if this was an acid in here and I was dripping it into a sample containing a base, then it would be the same shape of the graph. It would just be upside down. It would start at a high pH, and the pH would decrease as you added more acid. In this case, we've got an acid in our beaker, and we're adding base to it, which increases the pH over time. Okay, so at this point right here, this is where you're going to be at a pH of 7 if it's a strong acid with a strong base. That's the point at which you've finally neutralized all of the strong acid in there. At that point, you calculate how many milliliters it took to get there, and you can then go backwards and figure out how many moles of strong acid must have been in there and divide by the original volume of the sample, and you get whatever the original concentration of the strong acid was. You've done that before, but there's your refresher. So yeah, this is called the equivalence point. Let me write that in purple. This is what's called the equivalence point. Which is not necessarily the same point at which you end your titration. In fact, you will often miss the equivalence point by just a little bit, because even one drop of strong base might contain a little too much strong base to just neutralize the strong acid and not go past that. So you'll probably have some excess titrant, which is why usually you'll be somewhere like maybe up here. And this is what we call the end point. Now, as far as your calculations are concerned, if you're off by a drop, then that's probably not going to ruin your experiment, unless you're working for NASA or something. But if you're just doing it for academic purposes, then you're probably fine. The end point is probably a close enough approximation. The difference in volume is negligible. And this is why we can use phenolphthalein as an indicator. You might remember from the previous video. Let me actually pull it up again. Where is it? There it is. You might remember, if you look at the third item from the bottom, phenolphthalein changes color somewhere between 8 and 10 in terms of pH, somewhere around a pH of 9. And we use that to indicate the end point of our strong base, strong acid titrations. So it's perfectly okay to use that, because the difference between a pH of 7 and a pH of 9 is probably a fraction of a drop. Probably a fraction of a drop. Maybe recall earlier how dramatic of a change in pH we got with just, where did it go? Where did I put it? Oh, there it is. Missed it by one page. You might remember how dramatic of a change we got in pH just by adding 0.10 molar worth of sodium hydroxide. Even when we reduced it down to 0.010 molar of sodium hydroxide, we still had a pretty drastic change in pH from 3 to, I think our newer calculation gave us 12. But yeah, that drastic change in pH happens for a very specific reason. I guess we can actually look at this whole part of the curve. If we look at this whole section right here, this whole entire section, where it just seems to shoot up all of a sudden, the pH just kind of, it's climbing steadily up, 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 and then all of a sudden it just shoots up in a very short change in volume of titrant added, and then it goes back to increasing gradually again. So this is sometimes called the rapid rise, or I guess rapid drop if it was, titrating a base with an acid instead, if your curve was flipped. But yeah, this is sometimes called the rapid rise or rapid fall phase of the titration. And the reason it happens is actually pretty simple. As you continue to add more and more drops of your titrant, you're not changing the amount of additional hydroxide or hydronium per drop added. Each drop is roughly adding the same amount. It's probably a tiny amount, but it's still the same amount per drop, per milliliter. So when you get to this point, the concentrations of hydroxide and hydronium are low enough that even with the low amount of hydroxide or hydronium that's in your titrant, the effects on the concentrations in your beaker are going to be dramatic. When you're close to neutral, let's say you're around, pH of, let's say here's your pH of 6 is about here, and let's say your pH of 8 is around there. pH of 6 or 8, that would mean what? Let me do it in this little pocket over here. So when pH equals 6, that gives us hydronium concentration as 10 to the negative 6 and hydroxide concentration as 10 to the negative 8. When the pH is 8, it's the reverse. When pH equals 8, then you've got the exact opposite situation. Hydronium is at a concentration of 10 to the negative 8, and hydroxide is at a concentration of 10 to the negative 6. Those are really, really small concentrations. That's a millionth and I guess 100 millionth of a molar, respectively. 10 to the negative 6, that's 1 millionth. 10 to the negative 8 is a little more than a billionth. It's a 100 millionth. But if you're using a typical titrant concentration, maybe 1 molar, maybe 0.1 molar, something along those lines, let's say it's 0.1 molar. Let's say this was 0.10 molar of titrant. Well, how much is a drop? A drop is typically about around 1/10 of a milliliter. So 1 drop, where am I going to write this? 1 drop is approximately, it's not an exact science, but 1 drop is approximately 1/10 of a milliliter. So if I convert that to liters, that's 0.0001 liters. 0.0001 liters times 0.10 molar is 1 times 10 to the negative 5 moles. So 1 drop contains about 1 times 10 to the negative 5 moles of hydroxide or hydronium, depending on whether it's a base or an acid, respectively. Okay, that's probably not going to change the concentrations of hydronium and hydroxide that drastically near the beginning, where concentration of hydronium is pretty high, or at the end where concentration of hydronium is nearly non-existent and concentration of hydroxide is so big that you're not adding much to it. But in this middle range where the concentrations are small, where concentrations are like 10 to the negative 6 and 10 to the negative 8, adding 1 times 10 to the negative 5 moles of something is going to be pretty dramatic in comparison, and that's why you see this rapid rise. It's also the reason why using an indicator that changes color at a pH of 9 is no big deal. Oh, and I guess, come to think of it, if the end point I marked here is supposed to be a pH of 9, then my graph is not really to scale. But ignore that part. You get the main idea. Okay, so that's if you titrate a strong acid with a strong base. If you use the exact right quantities, then you can achieve complete neutralization where the pH is 7. If you use the exact right amount, achieving a pH of 7 at the equivalence point is to be expected. But what if you titrate a strong acid with a weak base, or a strong base with a weak acid? Wait, I think I worded that wrong. What if you titrate a weak base with a strong acid, or a weak acid with a strong base? Whatever your strong substance is, that should go in your, what's it called? Your burette. That should be your titrant. In that case, the curve changes a bit. So I'm going to continue with a strong base in my burette, but I'm going to change the contents of my beaker so that it has a weak acid inside. Okay, so we've got weak acid in here and strong base in here. All right, this changes the shape of the titration curve in a couple of different ways. In fact, do I? No, I don't need to draw it because I actually have one for you. Let me see, turn that off. Oh, and I guess I didn't even need to draw the first one either. I should have looked at my prepared slides before recording. I prepared these slides several weeks ago, so I probably should have checked what I had first. Anyway, there's your strong acid titrated with a strong base, which we already did, and then to the right you have titration of a weak acid with a strong base. So once you reach the equivalence point is actually going to be at a pH that is higher than 7. Should make sense, because if you put in equal moles of sodium hydroxide and some sort of monoprotic weak acid, if you put equal moles of those into a solution, then you will end up, well, let me actually work it out in front of you. So forget this, I don't need to draw this out for you, but if we had, for example, I don't know, 0.1, let's just use a generic acid. Let's say we had 0.10 molars of HA, and we reacted it with exactly 0.10 molars of sodium hydroxide so as to fully neutralize it. Then that would produce some water and the sodium ion and A-. So we'd have the conjugate base plus water plus the sodium ion, which is just going to be a spectator, so we can ignore it. Okay, but you're not going to be at a pH of 7 because things don't just stop here. Now that all of your sodium hydroxide is gone, your conjugate base can react with the water in the solution. So second step, water in the solution, and we did show this in the previous video. Your conjugate base can react with water in the solution to reform some of your weak acid and also generate some hydroxide ions, which would result in the solution being a little bit basic, which is equivalent to having a pH greater than 7 at room temperature. So yeah, the equivalence point and therefore the end point are going to be at a higher pH if it's strong base with weak acid, at a point lower than a pH of 7 if you were titrating a weak base with a strong acid. So the point is it's going to be a little off from 7, or maybe very off from 7, depending on how weak the acid or base is. If it's really, really weak, then you could end up somewhere really far away from 7. Okay, so that's one thing that changes. You do still have that rapid rise portion of the graph, though you probably won't see it if the acid or base is super weak. You probably won't see it if the acid or base is super weak. Let me actually show you this set of graphs from my book, if I can find the page where they actually have it. Give me a minute. Oh, there it is. Okay, yeah. This right here. So all of these are weak acids being titrated with sodium hydroxide. Let me move it up a little bit more. And you've got different weak acids being used, and they've drawn different curves. They've color-coded them. So, of course, you've got a strong acid with sodium hydroxide. You just get the usual shape. An acid with a Ka of 10 to the negative 2, not too much of a difference. A Ka of 10 to the negative 4 doesn't look too bad. A Ka of 10 to the negative 6 still goes up and has that rapid rise portion, but now you're seeing the rapid rise portion is getting smaller and smaller. Then you've got, when you try an acid with a Ka of 10 to the negative 8, you don't even see the rapid rise portion. It just kind of climbs at an angle. It just has a straight positive slope. And then with an acid whose Ka is 10 to the negative 10, you don't see anything. You don't even notice the equivalence point. You actually miss it. So you can't tell by looking at the graph where the equivalence point would be if your Ka is too low, if your acid is too weak. Similar situation if it was a weak base being titrated with a strong acid. So that's another thing that changes. And the third thing that changes is something that's not talked about a lot, so maybe you don't really need to know that much about it, but I think it's important. So I've highlighted a certain feature of this graph, which I've circled in green here. That right there, that initial little bump that initial little hump that you don't see with the titration of strong acids and strong bases together. It only happens when you're titrating weak with strong. What is that and why does it happen? This is something that's typically not explained in textbooks. In fact, I tried looking around online and it seems that people online are also confused about it, so there is a good chance that I might be the first notable online source that offers an explanation for this, in which case I guess that would be amazing, but I wouldn't be surprised if somewhere on some unknown website someone else has already answered it. So I'm not going to keep my hopes up too high. But let's talk about this and explain what's going on with these titrations in general. So I've already written down, if you've got a weak acid in here and you're titrating it with a strong base, then forget about the numbers I wrote down here. Forget about these numbers. Whenever you add a drop, this process happens until you run out of sodium hydroxide. A drop of sodium hydroxide gets in here, or whatever your strong base might be. It reacts until it's all gone with your weak acid, produces the conjugate base and some water and some spectator ions. Then, in another step, this equilibrium is established. So your conjugate base will decrease in concentration. Your weak acid will increase in concentration, and your hydroxide ion will increase in concentration. At least that's what happens initially. So, how do I word this for that little bump in the beginning of the titration curve? I guess I ended up drawing it after all, for this little thing right here. So I guess I need to break it down. So there's some point where once you cross this dotted line, everything continues like normal. But at this point, the pH seems to increase a lot after adding, let's say, the first milliliter, and increases a little bit more when you add the second milliliter, and then increases a little bit more when you add the third milliliter, and then afterwards things just kind of smooth out and it curves up like normal. So what is going on here? What's happening with those first few drops of sodium hydroxide being added? So for those first few drops, you're starting with some concentration of your weak acid, some non-zero concentration, a sizable concentration C. So you're starting with some concentration C. And in the first step, where the sodium hydroxide neutralizes it, you don't lose all of your weak acid because it's just a drop of sodium hydroxide. So it'll decrease by some amount. Let's call it x1. So you end up, when you come to step 2, you have C minus x1 as your concentration of weak acid. You've got, I guess, your concentration of weak base will then be equal to x1 at that point. And your concentration of hydroxide added would also be x1. No, wait a minute. Would it be? No, you haven't made any hydroxide at this point. Okay, so this is going to decrease, but it can't decrease by much. This is going to decrease, but it can't decrease by much because there isn't really much to go with. There isn't much conjugate base to get rid of to begin with, and you can't get rid of all of it, and even if you did, it's a really tiny amount. So what I'm trying to say here is that the concentration of A minus starts out low, while the concentration of HA starts out high, relatively speaking. And the concentration of OH minus, I guess, let's say we completed one cycle. Yeah, forget what I said here. So after one drop, after this equilibrium is established, you'll have a tiny bit of A minus, a high amount of HA, relatively speaking, and a tiny bit of hydroxide ion. So that's what you've got at the beginning. At the beginning, you haven't made much of this or much of this, but you do still have most of your starting weak acid. Okay, so in terms of Le Chatelier's principle, which way is the equilibrium going to shift when these concentrations start changing? Let's see, if you've got low concentrations here, that would help shift equilibrium more to the left. If you've got less reactant, then equilibrium will probably shift more to the left. Here you've got a sizable amount of product, that would shift equilibrium to the left, and you've got a low amount of reactant, that would shift equilibrium to the right. So we've got two factors that are telling us equilibrium lies more to the left. Two factors telling us that equilibrium lies more to the left when we're in this phase of the titration. In that case, wait a minute, that doesn't sound right at all. But then how would that explain? Let me think about this a bit. I know I thought it through before recording and I had a really simple explanation, but right now I'm just blanking on it. This would mean that we're producing a pretty large amount of a relatively large amount of hydroxide in the beginning, but this is after that first step. So after that, if we want to add more sodium hydroxide, produce more of A minus, now we've got these concentrations established, and that will after the first drop, since you already have some hydroxide ion and a high amount of your weak acid, that's going to, well, it's really the common ion effect, but you can think of it in terms of Le Chatelier. It's going to shift the equilibrium to the left, meaning that you're not going to get as much rightward progress as you did after the first drop. Okay, yeah, okay, it's coming back to me. So after adding the first drop, the next drop is going to suffer from a common ion effect that tries to keep the equilibrium to the left. You're still going to move right, because if you're adding sodium hydroxide, you have to move forward no matter what. It's just that you're going to be met with resistance, and that resistance just keeps on building up, and so the increase in pH from one drop to the next becomes less and less and less until you hit some point where you've added in a considerable amount of the conjugate base. You've created a considerable amount of the conjugate base, and now the situation is kind of reversed. Now you have a decent amount of conjugate base, and you've eliminated a lot of the weak acid, a lot being a relative term, but you've eliminated a significant amount of your weak acid. I wouldn't say it's low, but I would say it's now dropped down to a medium amount, and you've created a high amount of sodium hydroxide. I guess I'll just call this low to make it easier to understand. And now the factors favor going forward a little bit more and producing more sodium hydroxide. A high concentration of sodium hydroxide would try to push things further to the left, but a high concentration of your conjugate base would try to push things to the right. So you've got a push to the left and a push to the right, and if we consider the concentration of your remaining weak acid to have been lowered significantly, then that's probably another push to the right. So overall, the rate of increase in pH starts to climb back up again. Okay, hopefully that was an adequate explanation for the few of you who actually cared for an explanation. Again, this isn't really talked about by instructors or textbooks for that matter, so it's just for the truly curious. But there you go. So those are 3 things that differ when titrating weak acids and bases versus strong acids and bases. Some of you might be asking, well, what if I titrate a weak acid with a weak base, or a weak base with a weak acid? Too messy. Too messy, not a good idea. If you try to titrate a weak acid with a weak base, or vice versa, then good luck trying to perform calculations. We are actually going to do calculations for the titration of a weak acid with a strong base later. But yeah, good luck with this. Good luck with having a weak base as your titrant and a weak acid. I mean, if you use a pH monitor, then you'll be fine. But if you're trying to do calculations by hand related to this, have fun, because you need to make sure a bunch of different equilibrium processes hold at the same time. You need to make sure that 2H2O giving hydronium and hydroxide, you need to make sure that the concentrations of hydronium and hydroxide are such that the product of their concentrations is Kw. You need to make sure that this is true. So there's one equation. You need to make sure that HA plus H2O producing hydronium plus the conjugate base. You need to make sure that Ka is equal to the hydronium concentration times the conjugate base concentration over the acid concentration. You need to make sure that, let's see, I guess your conjugate base, well, no, not even your conjugate base. This might be an entirely different base. Let's call it B. So HA and B may not be conjugates of each other. B plus H2O gives us BH plus OH minus. You need to make sure this equilibrium holds, and you need to make sure that Kb is equal to concentrations of BH plus times OH minus over concentration of B. So already you've got those 3. equilibria need to hold. You've got a fourth equilibrium that needs to hold, because what if HA and B interact with each other? What if you have HA plus B giving you, let's see, that's going to be BH plus A minus. There's going to be some equilibrium constant for this, whatever it is, it's going to have to hold. So K equals concentration of BH plus times concentration of A minus over concentration of HA times concentration of B. Okay, so you need all four of those equations to hold, and how many variables do we have? We don't know the equilibrium concentrations of anything. So hydronium is a variable, the A minus is a variable, the HA is a variable, the hydroxide is a variable, the B is a variable, the BH plus is a variable. That's 6 variables and 4 equations. We might have more equations somewhere so that you can solve for all 6 of those unknowns, but yeah, that's a task better left to computers most of the time. So titrating weak acid with weak base, with the exception of maybe some special cases, and even then they don't ask about the special cases even at the college level. Usually the special cases are only brought up in those weird workbooks, the Barron's workbooks to be specific. I've never been able to get behind the Barron's philosophy of asking irrelevant questions. I mean, I get the idea of asking questions that are tougher than what will be on the exam you're preparing for and going in over-prepared, but irrelevant doesn't mean tough. Just because it's a hard problem doesn't mean it'll help you prepare if it's not relevant to the kinds of problems that you'd be doing. But that's my mini rant about Barron's and their workbooks. Let's move on. Let's actually look at some problems. I think we have a couple here. Is that the right set? I think so. 92. Explain how to choose the appropriate acid-base indicator for the titration of a weak base with a strong acid. Oh, okay. So, like we said, if you're titrating weak with strong, the pH at the equivalence point is not going to be 7. So, you're going to have to do some sort of initial calculation and make a prediction about where your equivalence point will be. If it's a weak base being titrated with a strong acid, then our equivalence pH is going to be below 7. The solution is going to be acidic overall. So I would have to pick from, let's look at my pH indicators again. Okay, so looking at those, I guess I would pick something maybe from the top half of that chart. Maybe brome cresol green, maybe methyl orange, maybe bromophenol blue. Or maybe I would use a mix of them. Actually, no, you'd have to know ahead of time what pH your equivalence point would be at. So you'd have to know that in advance so that you could pick an appropriate indicator. If you start mixing a bunch of them, that's not going to help. No, because then you'll be seeing the color changes, but you won't know if it's because you've reached the equivalence point or if it's because you've passed the equivalence point and you're just still changing the pH. But yeah, you'd have to know something ahead of time about the weak base that you're titrating so that you could figure out exactly what pH you'd be at when done titrating, and then pick the appropriate indicator based on that. And again, it doesn't have to be the indicator you pick. Its color change range doesn't have to actually include the pH that you're looking for. We explained with phenolphthalein, even though 7 is not within its color change range, we can still use it because overshooting the equivalence point by a drop or two is not going to be that damaging to your calculations. So that's 92. 93, explain why an acid-base indicator changes color over a range of pH values rather than at a specific pH. We kind of explained this in the previous video when we were talking about the, what was it called? When we were talking about the red cabbage indicator and acid-base indicators in general. Acid-base indicators are themselves acids and bases. They are capable of accepting or donating protons, and when they do so, they change their structure, which changes the colors of light that they absorb and or emit. So yeah, it's all about equilibrium. That's why there's a range of values rather than just a specific pH. It's what's the word I'm looking for? The color change happens as the concentration of, for example, if I use phenolphthalein, as you start shifting the equilibrium towards higher and higher pH, the concentration of the pink version of phenolphthalein starts to increase versus the clear version of phenolphthalein, whose concentration starts to decrease. So you shift the equilibrium such that you can see more of the pink and less of the clear colored version of the indicator. 94. Oh, and I guess continuing with 93. So it's a gradual process. It looks like it happens instantly, but it is a gradual process. It's not like all of your phenolphthalein turns pink instantly. It's just that enough of it turns pink and you lose enough of the clear stuff that you start seeing the color. And if you do it really, really carefully in the lab with a very diluted solution, then you can see the color of pink kind of start as a soft light pink and eventually get to a darker pink. But usually you'll just get a dark pink after that one drop that crosses you over. But if you use a really, really diluted solution, not something you're probably going to get the opportunity to do in the lab, but if you use a really, really diluted solution, you can definitely see lighter shades of pink and then gradually build up to that dark pink color. Okay, back to 94. Calculate the pH at the following points in a titration of 40 milliliters of 0.1 molar barbituric acid. Ka equals 9.8 times 10 to the negative 5 with 0.1 molar potassium hydroxide. And no potassium hydroxide added, 20 milliliters, 39, 40, 41. Okay, so sometimes you might have to determine a couple of data points and draw your own titration curve. So that's kind of what this is getting at, though it's not really asking you to draw the titration curve. Let me switch back to my document camera. So I like to think of these titration calculation problems as happening in 4 phases. Specifically, if it's a strong acid with weak base, or strong base titrating a weak acid. I like to think of the titration as happening in 4 different stages. And what was it? We were titrating a weak acid with a strong base in this case, so it's going to look like this. Okay, once you've gotten here, you've reached what's called the equivalence point, whatever volume that is. And then at half of that volume, I forgot to mention this earlier, but whatever this volume is, let's call it the equivalence volume. At half of the equivalence volume, 1/2 of the equivalence volume, you have what's called the half equivalence point. You have what's called the half equivalence point. The half equivalence point is not necessarily at half of the pH of the equivalence point, it's just at half the volume of the equivalence point. And there's something really, really special about it, which we kind of saw earlier. There's something special about the half equivalence point, but it is not necessarily, and often isn't, half of the pH at the equivalence point. So these 2 points are not directly related. There is no 1-to-2 ratio between them. The 1-to-2 ratio is between the volumes associated with them. But yeah, this is called the half equivalence point. Half equivalence point. And we'll see what goes on with that later, because I think this problem actually does have us do a calculation at the half equivalence point. Anyway, 4 different phases. So phase 1 is right here. This is the pre-titration phase. Phase 2 is everything between phase 1 and the equivalence point. So that's what I would call phase 2 of the titration. Phase 3 of the titration at the equivalence point, and then phase 4 is everywhere after the equivalence point. So that's what I would call phase 4. Now, knowing which phase you're in will help you determine how you're going to do your calculations to determine the pH. pH is over here, and this is going to be milliliters of, they told us it was potassium hydroxide. Okay, what did they give us? So they gave us 40 milliliters of 0.1 molar barbituric acid. So phase 1, we've got 40 milliliters, 0.040 liters of 0.100 molar barbituric acid. Barbituric acid. Okay, phase 1 is no titrant added. So essentially, you've just got 0.1 molar worth of barbituric acid in water. Okay, in that case, calculating pH is no different from what we've done in the previous video, and I think at some points towards the beginning of this video. We just use our K value, so in this case it's Ka equals, what did they say, 9.8 times 10 to the negative 5 equals, it's going to be x squared over c minus x. The x, I'll pretend it's negligible, and then we'll check and see if that assumption is correct. So starting concentration is 0.1. If I do 0.1 times 9.8 times 10 to the negative 5. That's 9.8 times 10 to the negative 6. That's not a surprise. And then take the square root of that to get x. So I should probably write I'm approximating this as x squared over c. So I get 3.1 times 10 to the negative 3. I get x equals 3.1 times 10 to the negative 3 molar. Is that negligible in comparison to 0.100? Let's see, 0.100 minus 3.1 times 10 to the negative 3. That's going to be 0.096 something. So I would say it's not negligible. I would use the quadratic formula to solve this one. Okay, this assumption is incorrect. To the quadratic formula we go, because they couldn't make this easy for us. Let's see, so if I work this out, it's going to be x squared will still be on the right-hand side. 9.8 times 10 to the negative 5. I'll just write it as Ka so I don't have to write out the whole thing. C is 0.1, so that's going to be 9.8 times 10 to the negative 6. That's when you multiply by C. Minus 9.8 times 10 to the negative 5x. I'll just call it Kax so I can squeeze it in there. Move those over to the right-hand side. We get 0 equals x squared plus Kax minus 9.8 times 10 to the negative 6. Okay, quadratic formula. Negative 9.8 times 10 to the negative 5 plus or minus the square root of 9.8 times 10 to the negative 5 squared minus 4 times 1 times negative 9.8 times 10 to the negative 6 all over 2 times 1. In the plus case, I get 3.1 times 10 to the negative 3. Wait a minute. That's the same as what we got earlier. And in the minus case, I get a negative, which is complete nonsense. Okay, 3.1 times 10 to the negative 3 was correct after all. Okay, x equals 3.1 times 10 to the negative 3 molar. Okay, that was correct after all. I don't know the formula for barbituric acid. Let me see if it's actually listed in the back of my book. If it's not, we'll just call it HA. Yep, not listed in my book. We'll just call it HA and be generic about it. So we had HA plus H2O giving A minus plus hydronium. So the X represents the concentration of your conjugate base, which I guess would be the barbiturate ion is what we'd call it, and the hydronium concentration. If X is equal to the hydronium concentration, take its negative log, and we have our starting pH. Negative log of 3.1 times 10 to the negative 3 is 2.51. So pH equals 2.51. All right, so that's phase 1, 0 milliliters of titrant added. Now let's figure out what the equivalence volume would be based on what we've got here. Assuming barbituric acid is monoprotic, then if you've got 40 milliliters of 0.1 molar barbituric acid and you're titrating with 0.1 molar potassium hydroxide, then at what point does the number of moles of potassium hydroxide added equal the moles of barbituric acid? In this case, since their molarities are equal, it would happen when the volume of KOH added is 40 milliliters. But generally speaking, we would use something that I showed you way back in video number 4. We would use N1V1 equals N2V2. Normality 1 times volume 1 equals normality 2 times volume 2. Normality being molarity times the number of equivalents. The number of equivalents is something we now refer to as the protonicity, since both our acid and base are monoprotic. N1 and N2 are just equal to M1 and M2. So we've got, I guess, instead of 1 and 2, I'll use A and B. Molarity of acid times volume of acid equals molarity of base times volume of base at the equivalence point. And yeah, since the molarities are equal, they'll cancel out, so the volume of base added needs to be 40 milliliters. That's where your equivalence point lies, at 40 milliliters of titrant added, which means our half equivalence point is at 20 milliliters. But the more important thing is between 0 and 40 milliliters will be in phase 2. And in phase 2, let's see, so part B wants 20 milliliters and part C wants 39 milliliters. Both of those are in phase 2. 20 milliliters happens to be the half equivalence point. I'm missing a marker. Oh, there it is. Or a Sharpie or whatever you want to call it. So let me see. What was I going to say? Oh, right. So in phase 2, you're at the stage where you have some of your strong base added to your weak acid, but not enough to neutralize all of it. You add some, but not enough to reach the equivalence point yet. So that's a recipe for a buffer. We talked about this earlier. One way to make a buffer if you don't have a salt of the conjugate is to use a weak acid with some strong base, or use a weak base with some strong acid. I think, yeah, we illustrated that here, I believe. Was it here? I feel like it was on this page. That might have been the... Yeah, there it is. Yeah, there it is. We had a weak base and we added some strong acid so that we still had some base left over, but also had some of its conjugate acid. So when you're in phase 2, you're basically in the buffer range. So that means you can just calculate pH using the Henderson-Hasselbalch equation. Now, if you're really, really close to the equivalence point and really, really close to the starting point, then Henderson-Hasselbalch is probably not going to work out too well for you. It's probably going to be a bad approximation. But usually when you're in phase 2, Henderson-Hasselbalch is the way to go. So pH equals pKa plus log of base over acid. And I guess we'll keep it as moles of base over moles of acid for the time being. Okay, so they wanted it at 20 milliliters, which is the half equivalence point. What's unique about the half equivalence point is that you've added exactly half the amount of strong base necessary to get rid of all of your weak acid. In other words, the moles of strong base you've added is equal to, where should I write this? I guess I'll do it here. At HEP, half equivalence point, moles of KOH added equals 1/2 the moles of acid that you started with. Okay, but if I'm adding a strong base to a weak acid, then that means I'm subtracting half the moles of the weak acid and creating an equal amount of moles of the conjugate base. So the final moles of acid is going to be the starting moles minus half, and the starting and the I think I worded that wrong. Let me say that again. Let me start that over. At the half equivalence point, the total moles of acid is going to be half of the starting moles of acid because you've neutralized half of it, and the total moles of base is going to be the same amount. It's going to be equal to half the starting moles of acid because that's how much acid you converted into the conjugate base. In other words, it's going to be a 50-50. It's going to be a 1-to-1 ratio, and the log of 1 is 0. So at the half equivalence point, pH equals pKa. pH equals pKa at the half equivalence point. So you can take a little bit of a shortcut if you know that. Okay, so then at 20 milliliters, the pH is going to be negative log of 9.8 times 10 to the negative 5. And that's going to be 4.01. So over here, pH is 4.01. And I guess I should mark my starting pH, which was 2.51. My vertical axis and probably my horizontal axis too are not drawn to scale, in case you were wondering. Okay, part C is asking us at 39 milliliters of potassium hydroxide added. So in this case, we can't take a shortcut. We do have to do some calculations. So let's see what we've got. It's still in phase 2. pH equals the pKa, which is 4.01, plus log of how many moles of base and how many moles of acid do we have. So our starting moles of acid, 0.040 liters times 0.1, that's going to be 0.0040 moles minus however much potassium hydroxide was added, 39 milliliters, and it's at a concentration of 0.100. So that means if you multiply those, then that's 0.0039 moles of potassium hydroxide that was added, so that's how much acid you've removed. And you started with 0 base, but by this point you've added 0.0039 moles of the conjugate base, because that's how many moles of the weak acid you have forced to convert. Okay, so that's going to go into our calculation. Log of 0.0039 over 0.0001. And that's going to be 1.6. That's going to be 1.6. So 4.01 plus, and it is positive 1.6, is 5.6. Is equal to 5.6. All right, so that's part C. Then they wanted at the equivalence point. At the equivalence point is pretty much the same as phase 1. At the equivalence point, essentially what you've done is you've forcibly gotten rid of all of the weak acid and converted all of it to weak base. So in phase 3, it's pretty much identical to phase 1, except now all you have is A minus, at least before the equilibrium is restored. All you have is A minus, and it will interact with the water to form some of your weak acid plus more hydroxide ion. And yeah, determining the pH here is the same as in step 1. You would calculate the, I guess, Kb value for this. So for conjugate pairs, Ka times Kb equals Kw. We've got let's do 1.0 times 10 to the negative 14 divided by 9.8 times 10 to the negative 5. That's 1.0 times 10 to the negative 10. Kb equals 1.0 times 10 to the negative 10. Set that equal to, I don't want to treat it as the same value as we had over here, so let's call it y. Y squared over C minus y. Oh, actually, I shouldn't call it C. Let's call it, let's call it C star minus y. So this concentration is going to be a little bit different because now we're at a different volume. So we're going to have to calculate the total volume. The initial volume of the acid solution was 40 milliliters, and the equivalence point was reached by adding another 40 milliliters of your potassium hydroxide. So now the total volume is 80 milliliters. The total moles is still, what was it, 0.0040, but now it's over twice the volume. So this concentration, C star, is going to be equal to half of the concentration that we had at the beginning, half of 0.100. So that's going to be 0.050 molar. Okay, they gave us an easy one where the volume just doubled, which means the concentration is half. But for harder ones, take the moles, divide by the new number of liters, and there's your molarity at the equivalence point. Okay, y squared over c star minus y. Since that's 1.0 times 10 to the negative 10, I think we'll be very safe in assuming that the y is negligible here. So I'll say it's approximately y squared over c star. And let's continue this on another sheet. So 1.0 times 10 to the negative 10 equals y squared over, what was it, 0.050 molar. And to be clear, y is going to represent the amount of HA and the amount of hydroxide, which is what we really care about. Okay, so 1.0 times 10 to the negative 10 times 0.050. Take the square root of that. And that's about 2.2 times 10 to the negative 6. Y equals 2.2 times 10 to the negative 6, which is definitely really small in comparison to 0.050. So our assumption to neglect it in the denominator was valid. Oh, right. So that's our hydroxide concentration. We can take the negative log of this to get the pOH, and then 14 minus that to get our pH. Negative log of 2.2 times 10 to the negative 6 gives us a pOH of 5.66. pOH equals 5.66, which means pH at the equivalence point is 14.00 minus 5.66 is 8.34. Our equivalence pH is 8.34. Well, not molar. It doesn't have units. I don't know what I was doing there. 8.34. And now that we know this, we can pick a suitable indicator. Now that we know that the equivalence point is at a pH of 8.34, we can pick an indicator that operates at or near that number, that either includes this number in its range or its range is close enough to that number. Okay, so that's phase 3. And then 41 milliliters of potassium hydroxide added. So that's phase 4. I guess I would call that the excess phase. So for this, to determine the pOH, you're going to need to calculate the excess hydroxide. So if we've added 41 milliliters of hydroxide, that's equivalent to 0.0041 moles, because it was at a 0.100 molar concentration. So 41 milliliters of KOH is 0.0041 moles. And let's see, that means, well, 0.0040 of it is used up getting us to the equivalence point, getting rid of our weak acid and neutralizing it. So, yeah, I guess I'll just write it. So, 0.0041 moles of KOH with 0.0040 moles of barbituric acid gives us some barbiturate ion plus potassium ion plus water. And yeah, you lose all of this, you lose most of this, you get a bunch of this, and we're left with 0.0001 moles of potassium hydroxide left over, which then just dissociates separately into potassium ion and hydroxide ion, creating 0.0001 moles of each. Okay, so we've got 0.0001 moles of hydroxide ion divided by what's the volume of the whole thing at this point. It was a 40 milliliter acid solution, and at this point we've added 41 milliliters of potassium hydroxide to it, so that's 81 milliliters in total. 0.0001 divided by 0.081 liters will give us our hydroxide concentration as, and this is going to come out to 1 sig fig, which feels really silly, but that's how they set up the problem. 1.0 times 10 to the negative 3. 1.0 times 10 to the negative 3. I feel inclined to just ignore the sig fig rules and write down 1.2 times 10 to the negative 3, but it is what it is. We'll stick with the sig fig rules. Okay, that gives us a POH. Remember, this is the hydroxide concentration. That gives us a POH of, oh, actually it's not even 1.0, it's just 1 times 10 to the negative 3. Anyway, that gives us a POH of 3.0, which is equivalent to a pH of 11.0. Now, some of you might be wondering why I didn't add the hydroxide that comes from the dissociation of my barbiturate, because now I've got 0.0040 moles of the stuff. So why didn't I repeat this process from phase 3? Because it's not going to contribute a lot of hydroxide anyway. I mean, if we take a look at phase 3, how much hydroxide did we get? We got 2.2 times 10 to the negative 6 molar, which is nothing in comparison to 1 times 10 to the negative 3. It's on the order of 1/1000th as big. So it's a very, very negligible amount. Even more negligible now because having this excess hydroxide creates a common ion effect, which will result in less hydroxide being generated from the dissociation of your barbiturate ion. So once you're in phase 4, once you're in the excess phase, you pretty much only have to calculate how much leftover hydroxide there is from your titrant, and that'll be all the hydroxide you need to calculate the POH and then the pH. And of course, opposite's true if we were using a strong acid as our titrant with a weak base. But yeah, there you go. So those are the 4 phases for titrations. At least that's the way I like to organize it. I don't think that's an official thing that is recognized in textbooks. Then again, maybe it was mentioned in a textbook and I'm just not remembering it. It's not like I have to review this all that often. I mean, I get to teach it to students every year, so it stays fresh in my mind. There are certain little tidbits here and there that you do need to review every now and then. Small facts that are hard to hold on to in memory, but a lot of the skills do stick with me. And I would hope that you try and strive to learn in a way that allows your skills to stick with you. It's not just about memorizing information, it's about developing skills. Okay. There's problem 95. Let me give it a read. The indicator dinitrophenol is an acid with a Ka of 1.1 times 10 to the negative 4. In a 1.0 times 10 to the negative 4 molar solution, it is colorless in acid and yellow in base. Calculate the pH range over which it goes from 10% ionized, colorless, to 90% ionized, yellow. Interesting. So we've got its Ka value. We've got the concentration of the solution, or the starting concentration in other words. Let's see, 10% ionized and 90% ionized. So, okay, yeah, that's not going to be that hard at all. We don't need to do ice tables or any of that. If they've given us the percent dissociation, or percent ionization as this book likes to call it, then yeah, calculating the other stuff. Okay, let's do it real quick. And then we need to go back because I forgot to mention something when we were talking about titrating a weak acid with a weak base or vice versa. There was one other thing that I forgot to mention, which was predicting whether a reaction of this form is going to have its equilibrium lie to the right or to the left. It was something that was brought up in the previous video, and I mentioned that I was going to delay it until this video, so I better make sure to cover that after we're done with this problem. Okay, so Ka equals, since we don't know the formula for it, it's just going to be generic A minus times hydronium over HA. And since we're solving for pH, I'm going to rearrange this. Solve for the hydronium. This should look familiar. We did do it before. Ka times HA over A minus. Oh, is it? Yeah, it's going to reduce to the Henderson-Hasselbalch equation, isn't it? Oh, well, yeah, because 10% and 90% ionization, those are 10 to 90 or 90 to 10. Well, 1 to 9 and 9 to 1 conjugate acid-base ratios. Yeah, that's in buffer range. Okay. Okay, that's in buffer range. So Henderson-Hasselbalch equation applies here, but we don't even need that because we already know what HA is going to be. It's 1.0 times, well, it starts at, okay, Henderson-Hasselbalch it is. pH equals pKa plus log of A minus over HA. All right, so in one case it's 9 over 1, in the other case it's 1 over 9. 90% ionized would mean that the amount of base is 9 times the amount of remaining acid, and 10% ionized would be the opposite. So pH equals, okay, all that attempt at derivation was for nothing. Should have previewed this problem. Negative log of 1.1 times 10 to the negative 4 is 3.96. 3.96 plus log of, I'll do 9 to 1 first, or 90 to 100, and then 100 to 90. So 3.96, actually wait, no, log of 90 over 100 is negative 0.05, negative 0.05, so that's negative 0.05, and if I flip it over, that's going to be positive 0.05. So that means that the pH range where color change can happen is going to be at a pH of 3.96 plus or minus 0.05. So that's going to be between 3.91 and 4.01. That's the range at which a color change can happen for dinitrophenol, if I'm understanding this problem correctly. And I guess knowing that it was a 1.0 times 10 to the negative 4 molar solution was pointless. We didn't need that value at all. Okay, good to know. Now then, like I said, how do we predict which way equilibrium lies when dealing with, actually there's enough space for it down here, probably. If I have a weak acid with a weak base that are not conjugates of each other, and I want to determine whether this reaction will favor the right-hand side or the left-hand side. How do we make that prediction? I may have mentioned very briefly in the previous video without explanation that the side with the stronger acid is the less favored side. So let's call the equilibrium constant for HA, let's call that Ka, and equilibrium constant for B, let's call that Kb, and then A minus, that's the conjugate base of HA, so I'm going to call its equilibrium constant Kcb, C standing for conjugate, so conjugate base, and for BH plus, that's a conjugate acid, so Kca. So, in other words, what we've established here is Ka times Kcb. These are related and are equal to Kw. And similarly, Kb and Kca. Those two are related. Their K values multiply to Kw. Okay. So we're going to take advantage of those two facts. Equilibrium lies with whichever side has the weaker acid. So if I compare HA with BH+, if I compare the two acids, if the acid on the right-hand side is weaker than the acid on the left-hand side, then equilibrium will favor the right-hand side. If the opposite is true, it'll favor the left-hand side. I could also do it based on the bases. I could also say that if the base on the right is weaker than the base on the left, then the equilibrium will favor the right, and if it's the base on the left that's weaker, then equilibrium will favor the left. But usually we just focus on the two acids because it really doesn't matter. How do we determine which acid is stronger or which base is stronger? We just compare the K values. If Ka is greater than Kca, then equilibrium will favor the right. If it's the opposite, then equilibrium will favor the left. Similar reasoning can apply to these two. And you might be wondering, well, what about the bases? Why can we just ignore the bases and just focus on the acids, or ignore the acids and just focus on the bases? There's a really, really simple what's the word I'm looking for? There's a really simple mathematical relationship that proves that you only need to make one comparison, acids to acids or bases, acid to acid or base to base. So let's say that equilibrium favors the right. It doesn't really matter. You can repeat all the steps I'm about to show, but with the opposite assumption, and you'll see that that's true as well. If we assume that Ka is greater than Kca, if Ka is greater than Kca, if the base on the left is stronger, if the acid on the left is stronger than the acid on the right, then it's the same thing as the base on the left being stronger than the base on the right. If the acid on the left is stronger, then the base on the left is also stronger every single time. We can prove it mathematically. If Ka is greater than Kca, then we can say that, how am I going to work this out? Then we can say that 1 over Ka is less than 1 over Kca. If Ka is bigger than Kca, then of course if you flip them over, if you take their reciprocals, then the relationship also flips. If that still doesn't make sense to you, consider just dividing both sides by Ka and dividing both sides by Kca, and you'll get 1 over Kca is greater than 1 over Ka. Okay, let's multiply both sides of this by Kw. So this is the same as saying Kw over Ka is less than Kw over Kca. What's Kw over Ka? Well, that's Kcb, according to the definition that we gave here. That's Kcb. So I guess I'll do that in dark green. So that's Kcb is less than Kw over Kca. Well, that's just Kb. So if Ka is greater than Kca, Kb is greater than Kcb. Easily proven. Easily proven. And I guess for some intuition as why this should be true. If this is the side with the stronger acid, then the stronger the acid, the weaker the conjugate. So if this is a stronger acid, relatively speaking, then its conjugate is going to be a weaker base. The stronger this is, the weaker this is. So if you have this side having the stronger acid, it necessarily makes the opposite side have the weaker base. We already know it has the weaker acid because that's the initial comparison that we make. But it also establishes at the same time that the base on the right-hand side is also weaker. And of course, if the acid on the right-hand side is actually stronger, then that also necessarily means that the base on the right-hand side is stronger. So it works in either of the two possible cases. Okay, so that takes care of that. Let's have a look at the other major part of this chapter, or, well, I guess it's the next chapter technically if you go by the digital book. Let's take a look at solubility equilibria. Equilibrium involving solubility. Solubility equilibria. We're still dealing with weak electrolytes, but this time the weak electrolytes we're looking at are not necessarily acids or bases. Most of them are salts. Some of them might function as acids and bases. We'll talk about that a bit at some point towards the end. Well, maybe not necessarily towards the end. At some point in this video. Solubility equilibria. So equilibrium processes involving solubility. There was a time back in video number 4 when we said things like all nitrates are soluble, all acetates are soluble, all chlorides, bromides, and iodides are soluble except when paired with silver, lead 2 or mercury 1 ions. And we would say something like silver chloride, we would say that it's insoluble. We would call it insoluble. And of course that isn't really the truth. It's not truly insoluble, it's just that its solubility is very, very low. I think I may have mentioned that in that very same video, but if not, then I believe I mentioned it in video number 11 that was focused on solutions. But yeah, insoluble, what it really means is very low solubility. Low solubility. And why is the solubility low? Equilibrium. And equilibrium is reached before you can dissolve all of your silver chloride or whatever salt you have. So the dissociation or solvation of solid silver chloride is going to give us some amount of silver ion and some amount of chloride ion. Equilibrium lies very heavily to the left, so I guess one way you could represent that is you could write the bottom arrow that points to the left way bigger than the top arrow that points to the right. I don't think I've done that at all in the past 3 videos. I probably should have, but if you see this sometimes in textbooks, that's just a way of communicating where the equilibrium lies, which side is preferred, products or reactants. Anyway, so these are both going to be in the aqueous phase. They are going to count towards the equilibrium constant, and the solid doesn't count. So The equilibrium constant for this is given a special subscript, Sp, which stands for solution product or solvation product. So it's going to be concentration of silver times concentration of chloride divided by, well, there's nothing to divide by, because on the reactant side, you've got a solid. Okay, so the KSP value for silver chloride is going to be how much? Let me check. I think it's 1.8 times 10 to the negative 8. Silver chloride. 1.8 times 10 to the negative 10. Equals 1.8 times 10 to the negative 10. Okay, so if I were to put some solid silver chloride in some pure water, then only a tiny amount would dissolve. There's an illustration of silver chloride. Yeah, it is silver chloride. Okay, I chose a good example, matched with my visuals. So yeah, very, very tiny amount of silver chloride gets ionized. You see a few particles over there on the right-hand side that are floating about, while the rest is still intact within the crystalline structure. So if I put some of this in pure water, then of course you're going to have an excess amount of it. We don't really care how much because it doesn't affect the equilibrium anyway. It's going to decrease by however many, well, it's not really a molar amount per se, but it's a number of moles that once you divide it by the liters gives you the number of molars. So X is still in units of molarity, even if solids don't have a molarity to them. And these would each start at 0 and increase by X. And there you go, putting your quote-unquote insoluble solid into pure water will just produce 0 plus X to the first power times 0 plus X to the first power. X times X is X squared. X squared equals 1.8 times 10 to the negative 10. If we take the square root on both sides, then that's 1.3 times 10 to the negative 5. X equals 1.3 times 10 to the negative 5. And that's in units of molarity. And sometimes this X value is actually called S. And it's given the name molar solubility. Molar solubility. It's the solubility in units of molarity. Molar solubility S. And of course, this is the molar solubility in water. We can also try the molar solubility in things like acids, for example. What's the molar solubility of still silver chloride, but let's say it's not in pure water this time. Let's say we've got silver chloride in, let's make it 0.50 molar hydrochloric acid. Well, your 0.50 molar hydrochloric acid gives you a starting chloride concentration, initial chloride concentration, equal to 0.50 molar. You get 1 chloride for every 1 HCl after all. Okay, so now the math is a bit different. But we've seen this before. What's going to happen to the molar solubility this time? Will it increase or decrease? It involves a concept we discussed in this video. It will decrease because of the common ion effect. The solution that your silver chloride is being added to has an ion in common with silver chloride. In this case, it's the chloride ion. So you have an excess amount of this. It'll decrease by some amount x. This starts at 0, increases by x. This starts at 0.50, increases by x. It's still the same KSP value, so 1.8 times 10 to the negative 10 equals silver to the first power, so 0 plus x is x. Chloride to the first power as well, that's 0.50 plus x. Okay. The x that we got before was 1.3 times 10 to the negative 5, which is negligible in comparison to 0.50. Now that we've got the common ion effect, this x is going to be even less than the previous x, so even more negligible. We can just approximate this as 0.50. So we can say 1.8 times 10 to the negative 10 equals x times 0.50 approximately. Divide by 0.50, 1.8, well, I guess that's going to be 3.6 times 10 to the negative 10. So x is going to be 3.6 times 10 to the negative 10 molar. Even less soluble than before. So solubility of silver chloride and hydrochloric acid much lower than its already low solubility in pure water. So definitely make sure you know the difference between when you're calculating molar solubility in pure water versus molar solubility in some solution that may or may not contain common ions. Very important to tell the difference between which of the two you're looking at. I've seen students get really confused about this for whatever reason because they get into the habit of calculating molar solubilities in pure water, which are easy to do and easy to set up. In fact, I'm going to argue that you should learn to set these up in under 15 seconds in a minute. And yeah, for whatever reason, when you throw this curveball at them, they get lost and don't know what to do. I'm not really sure why this is happening with students. Maybe it's the way that teachers teach it. They just kind of assume the students will know and they don't point it out. But I think it's simple to tell which of the two cases you're dealing with. So maybe it really is just the act of pointing it out that some teachers assume it's so obvious there's no need to explicitly point it out. Okay, so I'm going to argue that you need to be able to quickly set up the equation for calculating molar solubility for a weak electrolyte that is that's placed in pure water, for an excess amount of weak electrolyte that's placed in pure water. Okay, we've got, let me list some examples here. We have barium carbonate, barium fluoride, let's see. Lanthanum iodate. What else should I pick from here? Zinc hydroxide. Okay, and here are their KSP values. So for barium carbonate, it's 5.0 times 10 to the negative 9. For barium fluoride, it's 1.7 times 10 to the negative 6. For lanthanum iodate, it's 6.1 times 10 to the negative 12. And for zinc hydroxide, it's 3.0 times 10 to the negative 16. Okay, let's try and determine the molar solubilities for each of these. And it might be worthwhile to pause and make predictions about which one is going to have the highest and which one's going to have the lowest molar solubility. In fact, maybe try ranking them. A common mistake that I see is that students will rank them just based on the KSP values alone. The lowest KSP must have the lowest solubility, right? Well, there's more to it than that. There's more to it than that. But yeah, some people would predict that this would be the lowest, and then this would be the third, and this would be the second, and they would predict that this would be the highest. But that's not always going to be the case. We're going to compare against our simple predictions, our naive predictions in a bit. So you have to write out the equation. Well, you don't have to. With enough practice, you'll be able to quickly see it in your head and figure out the molar solubilities in under 15 seconds. Some people might be intimidated when they first hear that, but I'm not saying it because I have high standards. I mean, I do have high standards, but that's not the reason I'm saying it. I'm saying it because it really is that easy. Anyway, barium ion plus carbonate ion. I'm not going to list the phases every single time. I mean, solid on the left, aqueous on the right. That's how it's always going to be. Barium fluoride gives us barium ion and 2 fluoride ions. Lanthanum iodate gives us the lanthanum 3 ion plus 3 iodate ions. And zinc hydroxide gives us zinc ion plus 2 hydroxide ions. Okay. if I dunk each of these into pure water, then you start with excess amounts of solid. They decrease by x, or in this case I'll call it s. These start at 0 and increase by, this increases by s, and this increases by s as well. Nothing too different from our first example with silver chloride. And then you would say that KSP is equal to, this is s and this is s, so s squared. All right, what about barium fluoride? So you start with an excess amount, decreases by s. This starts at 0, increases by s. Fluoride starts at 0, increases by 2s. Remember the balancing coefficients. And so KSP is going to be equal to, for barium it's s, times, for fluoride it's 2s. And remember, balancing coefficients become exponents, so you square that. So that's s times 2s times 2s is 4s squared, so that's equal to 4s cubed overall. Ah, that throws a wrench in things. Okay, lanthanum iodate, xs minus s. This will increase by s from 0. This will increase from 0 by 3s. And so KSP equals, lanthanum is s times iodate is 3s, and because it's 3, it's also cubed. It's also cubed. So 3s times itself 3 times, that's 27s cubed, so we've got s times 27s cubed, which is ultimately 27s to the 4th. All right, and our last one, zinc hydroxide. Can you immediately tell that it's going to be 4s cubed? That took me less than 5 seconds, let alone 15. I think 15 is very reasonable. 0 plus s, that's 0 plus 2s. So that's going to be KSP equals s for zinc times the square of 2s for hydroxide. We already know how this ends, 4s cubed. All right, let's actually calculate the s values then. So KSP equals s squared. S is the square root of 5.0 times 10 to the negative 9 for the first one. Square root of 5.0 times 10 to the negative 9 is 7.1 times 10 to the negative 5. 7.1 times 10 to the negative 5. Okay. Next one, barium fluoride, 1.7 times 10 to the negative 6 is equal to 4s cubed. So divide by 4 and take the cube root. 1.7 times 10 to the negative 6 divided by 4. Remember that the 4 here is an exact number. And then take the cube root of all that. If you don't have a cube root function on your calculator, then just raise it to the 1/3 exponent. So you would just take KSP over 4, and then raise it to the 1/3. And that's how you would take a cube root. Okay, and that's 7.5 times 10 to the negative 3. Okay, lanthanum iodate. So divide by 27 and take the 4th root because it's 27s to the 4th. 6.1 Oh, let me put it in parentheses first. 6.1 times 10 to the negative 12 divided by 27, and then all that raised to the 1/4 power. And that's 6.9 times 10 to the negative 4. And then for zinc hydroxide, 4s cubed equals 3.0 times 10 to the negative 16. So in parentheses, 3.0 times 10 to the negative 16 divided by 4. And then close parentheses, raise that to the 1/3. And that's 4.2 times 10 to the negative 6. And I guess all of these are in units of molarity. So yeah, that's the maximum molar concentration of each of those substances that you can have. Only achievable if you put them in pure water. If you put them in solutions, well, not necessarily just pure water, but in solutions that don't have common ions. In the absence of common ions, that's how much you can get. In the presence of common ions, you get less. And sometimes you can get more if you use strong acids or strong bases as your solution. But we'll talk about that in a bit. What was I going to say? Oh, right. Let's check our predictions. So we predicted that barium fluoride would have the highest molar solubility. That did turn out to be the case. 7.5 times 10 to the negative 3 is bigger than all those other ones. So that prediction was correct. We predicted that barium carbonate would be next. And that prediction is wrong because 6.9 times 10 to the negative 4 actually comes first. 6.9 times 10 to the negative 4 is greater than 7.1 times 10 to the negative 5. So this prediction was wrong. It's actually ranked number 2 from highest to lowest. And this would end up in 3rd place then. That would put this in 3rd place. And then the zinc hydroxide would have the lowest molar solubility. But the point is you cannot just use the KSP values to predict which substance has the highest or lowest molar solubility. You do have to work it out. You do have to actually calculate the molar solubility. It's not enough to just compare KSP values, unless you are comparing substances that yield the same set of balancing coefficients. So if I was comparing barium fluoride and zinc hydroxide, which give me balancing coefficients of 1, 1, 2, 1, 1, 2, that's fine. For those two, I can compare them directly based on KSP values. But if you're comparing two substances that don't have matching balancing coefficients when you write out the equation, then you will have to just work out the whole thing and solve for the molar solubility. Not that it's going to be that hard to do. So, for the pure water case, I argue that you should be able to get these KSP equals s squared, KSP equals 4s cubed, KSP equals 27s to the 4th, and so on. You should be able to get this in 15 seconds or less, just in the pure water case. If you have common ion effect going on, then all that goes out the window and you might have to be more careful. but at least in the pure water case, I do expect you to get to the level where you can get this done in under 15 seconds just by looking at the solid. You don't even have to write out the equation. If you need to be at the point where you can see the equation immediately in your head and quickly figure out what goes on the other side of the equal sign beside the KSP. So let's just take a look at a couple of examples to show you how quick this should be going. If I pick at random, let's do magnesium hydroxide, MgOH2. Okay, I see a 1, I see a 2, so that's going to be an S and a 2S squared. That's going to be 4S cubed equals KSP. Okay, pick another one at random. Calcium sulfate. Calcium sulfate gives me a calcium ion and a sulfate ion. So that's going to be a 1 and a 1, an S and an S. S squared equals KSP. It's on video. You can time it. That's less than 15 seconds. That's probably less than 10 seconds. It is that easy. Lanthanum fluoride. Let's see, 1 and 3, so that's going to be S, and 3S cubed. That's going to be S times 27S cubed. That's going to be 27S to the 4th equals KSP. And I'm deliberately slowing down so that you can actually follow what I'm doing. If I were doing this alone, it would be even faster, because I've memorized that 3S cubed is 27S cubed. I've memorized that this is this, so I wouldn't even write that middle step. I would skip straight to this if I were doing it on my own. In fact, if I were doing it on my own, I wouldn't even write these first steps. But, you know, if you need to include those steps, you can still get it done in under 15 seconds. I don't think that's too much to ask for. I remember one time I had a student, I told her that she had to get these in under 15 seconds, and later in class, apparently she was studying that, and one of her classmates asked her what she was doing. And she said, "Oh, I'm trying to figure out these KSP problems and set them up in less than 15 seconds. And then a student overheard them and freaked out and said, "We have to do them in less than 15 seconds?" And yeah, so I caused some mayhem in a classroom far, far away. I'm very proud of that. Anyway, let's take a look at some things we can do with these KSP values now that we have them. Let's take a look at some problems. Wait, do I need... No, I don't need anything from there anymore. Well, maybe one more thing for later. Let's look at some problems to walk us through how this KSP stuff works. So that first problem, we've seen something similar to it 2 videos ago. It's just the change row of your ice table. That's really all it is. You know how to do it. We've seen this before. I'm just gonna move on. If you want to practice it, pause the screen. Same goes for problem number 2. What does problem 3 say? How do the concentrations of silver and chromate ion in a saturated solution above 1 gram of solid silver chromate change when 100 grams of solid silver chromate is added to the system? Explain. There should be no change. There should be no change. I'm pretty sure we talked about something similar to this before, but I'm blanking out on what exactly it was and what the context was. But if you already have a saturated solution of silver chromate then that's it. Adding more solid silver chromate has no effect on the equilibrium. It doesn't shift it to the right, doesn't shift it to the left. Solids and liquids have no effect. Number 4. How do the concentrations of lead ion and sulfide ion change when potassium sulfide is added to a saturated solution of lead sulfide? In that case, if it's a saturated solution, that means that it's at equilibrium. And if it's at equilibrium and you add potassium sulfide, so basically the sulfide ion, you're increasing the concentration of products, which according to Le Chatelier's principle would cause equilibrium to shift to the left. What does it mean for equilibrium to shift to the left? It would mean that your ions, some of them, are turning back into solid. What do we call that? We call that precipitation. So precipitation will occur if you add potassium sulfide to a saturated solution of lead to sulfide. Speaking of sulfides, I should probably mention this. Sulfides are kind of special. So if you have metal sulfides, then they decompose into 3 ions. They decompose into 3 ions because it's actually a reaction with water. So you'll get the metal ion, usually it's going to be a positive 2, plus the hydrogen sulfide ion plus plus hydroxide. So you actually get 3 products in this case. And, well, lead sulfide, so that's lead 2 sulfide. Maybe that's not the best example. If I had something like silver sulfide, Ag2S, then that would react with water, giving us a silver ion, 2 of it, plus the hydrogen sulfide ion plus hydroxide. And is that balanced? Yeah. So that's a special case for sulfides. You're probably not going to end up dealing with it because I know I've never had to deal with it at any level of my chemistry education. I don't think AP deals with it. I don't think IB deals with it. I don't think that college general chemistry courses have you deal with it, but there it is just in case. Just in case. Metal sulfides have a unique dissociation. Back to problems. Problem 5, what additional information do we need to answer the following question? How is the equilibrium of solid silver bromide with a saturated solution of its ions affected when the temperature is raised? Okay, so Le Chatelier tells us that when the temperature is raised, the equilibrium shifts to the right if the process is endothermic and to the left if it's exothermic. So what we really need to know is whether or not the dissolution process of, what was it, silver bromide? Yeah, whether the dissolution of silver bromide is exothermic or endothermic. That's the missing piece of information. Usually, though, increasing temperature will increase solubility. So if you had to guess, that's what I would go with. But there are cases where increasing the temperature might actually lower solubility. Number 6. Yeah. Which of the following slightly soluble compounds has a solubility greater then that calculated from its solubility product because of hydrolysis of the anion present. We've got cobalt 2 sulfite, copper 1 iodide, lead carbonate, lead chloride, lead 2 chloride, I should say. Tellurium sulfide is tellurium. Or no, not tellurium. I think that's thallium. I think TL is thallium. Let me check the name. I'm looking at a periodic table that doesn't have the names in the table, but in a separate chart. Yeah, it's thallium. TH is thorium. Okay. So that's thallium 1 sulfide and then potassium perchlorate. It would be the thallium 1 sulfide. We just talked about this. So it's going to have a higher Yeah, I guess this book doesn't recognize the process I just listed here. The book that these problems come from, I guess, has you do Ag2S separating into 2 Ag plus and 1 S2 minus. And then in a separate step, they have the water react with the sulfide ion to form the hydrogen sulfide ion plus hydroxide ion. Wait, is that a plus? No, that's supposed to be a minus. Okay, and yeah, this process is called hydrolysis. So that's what they mean there. So they think of it as, and I guess I'll write the metal dissociation as a separate step too. So Ag2S dissociates into 2 Ag plus S2 minus, and then H2O comes in and the sulfide is hydrolyzed. Rather than put it all into one step like I have up here in orange, you can think of it as those two separate steps. And if you do think of it as those two separate steps, then you can think of this first step as having sulfide removed from it by the second step. So you can think of hydrolysis as removing product, lowering its concentration, shifting this equilibrium further to the right. So that's in Le Chatelier terms. Is number 7 the same? Yeah, number 7 is the same. It's the zinc sulfide. Okay. Next set of problems. Write the ionic equation for dissolution and the solubility product expression for each of the following. We've already seen how to do that. Number 9 is the same. We'll skip. Number 10, Handbook of Chemistry and Physics, linked over there, gives solubilities of the following compounds in grams per 100 milliliter of water. Because these compounds are only slightly soluble, assume that the volume does not change on dissolution and calculate the solubility product for each. Okay, so basically instead of the solubility given in units of molarity, it's given in different concentration units. Convert it to molarity and work backwards. Let's just do one of these. I'll do... Let's do B. Cerium 4 iodate. 1.5 times 10 to the negative 2 grams per 100 milliliter. Okay, cerium 4 iodate. So we've got cerium 4 iodate. Wait, was it iodate or per iodate? No, it was iodate, so IO3. Messed this up. CeIO3, 3. Okay, so KSP is going to be, we're putting this in pure water, so it's going to be, we get 1 cerium and 4 iodates. So that's going to be S times 4S to the 4th. 4 to the 4th is 256. So that's going to be 256 S to the 5th power. Okay. S is equal to, they gave us 1.5 times 10 to the negative 2 grams per 100 milliliter. Per 100 milliliters. We would just convert the grams to moles, calculate the molar mass of cerium, and convert the milliliters to liters. That would give you moles over liters. That would give you the molarity. Plug it in, raise it to the 5th power, multiply by 256, and you're good to go. I think you can take it from there. All right, next set of problems. 11, same as 10, we'll skip. 12, use solubility products and predict which of the following salts is the most soluble in terms of moles per liter in pure water. We already did something like that, so skip. Remember, you can't just base it off of the KSP values. You do have to calculate the actual molar solubilities. And also, remember for mercury, Hg2Cl2, the mercury 1 ion is a diatomic ion. So when it dissociates, you don't get 2 mercuries and 2 chlorides. You get a chloride, and you get the 2 mercuries are still paired up together. Oh, and I guess that means that all 4 of them are going to give you balancing coefficients of 1, 1, 2. So I guess in this very specific case, you can just compare them all based on KSP values. But remember, in general, KSP values alone don't determine solubility. 13, assuming that no equilibria other than dissolution are involved, calculate the molar solubility of each of the following from its solubility product. Okay, doesn't look like anything that we haven't covered before. I guess different compounds that you'll have to look up, but other than that, we know how to calculate molar solubilities in pure water. Moving on. (14), same as the previous. 15, assuming no, okay, same as the previous. 16, same as the previous. Oh, show that changes in the initial concentrations. Oh, we have common ions. Never mind. 15 and 16, it's not molar solubility in pure water. We do have the common ion effect, and it says show that changes in the initial concentrations of the common ions can be neglected. Well, we already saw an example of that, so I'll pass on this one. Okay, 17. Show that it is not appropriate to neglect the changes in the initial concentrations of the common ions. Here we go. Here we go. we need to see at least one example of this. Not that I doubt you'd be able to handle it without an example, but you know, for completion's sake. Which one, actually, we haven't decided. Which one should we do? I'll do barium fluoride. Barium fluoride in 0.0313 molar potassium fluoride. The potassium is just going to be a spectator ion, and yeah. So we've got barium fluoride in potassium fluoride. So KSP for barium fluoride, I think we had that one listed earlier. 1.7 times 10 to the negative 6. Okay, 1.7 times 10 to the negative 6 equals, barium is going to be X, and then fluoride is going to be 0.0313 plus 2x, and then that's going to be squared. Oh, is this even solvable by hand? I don't think it is, but we'll try. We'll try and see how far this can take us. So if I FOIL that, well, if you FOIL it and then distribute the x, if you FOIL it, you get a quadratic. If you distribute the x, you get a cubic. And yeah, solving cubic equations is not something you can do by hand. At least I don't know how to do it by hand. I think there's something similar to the quadratic formula for cubic functions, but I don't know it off the top of my head. So for something like this, you either wouldn't be asked about this in the first place, or you would be allowed to use a graphing calculator or equation solver to do it. But at least we saw how to set it up. So yeah, I guess we'll bail on that one. Is there one that's more doable? Calcium hydroxide in an unbuffered solution, initially with a pH of 12.700. If the X isn't negligible, it's going to pertain to the hydroxide, and the hydroxide has that same problem. Okay, yeah, that's not going to work. So I guess the only one that's really doable is the thallium chloride. The only one that's doable is the thallium chloride. That one we can do by hand. Okay, let's do it. So we'll bail on this. And we've got the thallium chloride, so it's just going to be the thallium concentration times the chloride concentration equals KSP. Do I even have the equilibrium constant for thallium chloride? I do not have it in this list. Let me look at my other list. I prefer the list in my physical book. The digital book did something really dumb, in my opinion. They listed all of these solids in single columns that barely take up even 30% of the page. They could have fit 3 columns per page, but Instead, they decided, no, we're going to make you scroll through page after page after page looking for the value that you want. But yeah, it looks like KSP for the thallium 1 chloride is 1.7 times 10 to the negative 4, and we've got 0.025 molar thallium 1 nitrate. So that's going to be equal to thallium to the first power, so that's going to be 0.025 plus x times chloride to the first power, that's just going to be x. Okay, 0.025 plus x times x. This is going to be a quadratic, still a pain to deal with, but at least it's doable. 1.7 times 10 to the negative 4. That's going to be 0.025x plus x squared. Subtract the 1.7 on both sides and rearrange a bit. So x squared plus 0.025x, and subtract the 1.7 times 10 to the negative 4. Quadratic formula. Let's see, negative b, so that's negative 0.025 plus or minus the square root of 0.025 squared minus 4 times 1 times negative 1.7 times 10 to the negative 4 all over 2 times 1. In the plus case, I get 5.6 times 10 to the negative 3, and in the minus case I get a negative number, which makes no sense. So 5.6 times 10 to the negative 3 molar. That's definitely not negligible. 0.025 plus 5.6 times 10 to the negative 3 is going to be 0.031. That is a significant change. That's more than a 20% increase in the concentration of the thallium 1 ion. Okay. So there's one example of that. 18. Explain why the changes in the concentrations of the common ions in exercise 17 can be neglected. Oh, no, not 17. They mean I think it was 15 and 16. Let me pull up the page again. Yeah, they mean for 15 and 16. Probably referring to 16. Yeah, that's what they're referring to. So 18 refers to 16, 19 refers to 17. Okay, so they misnumbered those. But you know, that's what happens with textbooks. So this is one of the legitimate reasons why textbooks always have multiple editions. Then there are not so legitimate reasons, like they changed the coloring on a graphic, so now you have to buy the brand new book and help the publisher make more money. If you buy a used version of the older edition, then they're not making a new sale, they're not making any extra money. That's the problem with textbooks. I'll probably post a link to a video that talks about that in more detail for those of you that are headed towards college or already in college and haven't realized yet what a scam textbooks are. Anyway, number 20, calculate the solubility of aluminum hydroxide in a solution buffered at a pH of 11. Okay, so the role of pH. pH allows you to calculate the concentration of hydronium or hydroxide. In this case, the common ion would be hydroxide, so I would convert to the pOH. And pOH here would be 3, assuming this is at room temperature, 3.00 to be more specific. And that would mean that your initial hydroxide concentration is 1.0 times 10 to the negative 3. And then from there, the rest is just like the previous problem we did. So aluminum would just start at 0 and increase by x. Hydroxide would start at 1.0 times 10 to the negative 3 and increase by 3x. Take the cube for hydroxide. Hopefully the 3x is negligible. Otherwise, you're going to need a graphing calculator or equation solver to do it. But yeah, with pH, nothing too different. You just have to use it to calculate the concentration of, typically it'll be hydroxide. Okay, 21, refer to Appendix J for solubility products of calcium salts. Determine which ones are most soluble. Okay, we did something like that. Most barium compounds are very poisonous. However, barium sulfate is often administered internally as an aid in the X-ray examination of the lower intestinal tract. This use of barium sulfate is possible because of its low solubility. Calculate the molar solubility of barium sulfate in 1 liter of water. We've already done that. 23. Public Health Service standards for drinking water set a maximum of 250 milligrams per liter of sulfate ion because of its cathartic action, which is to say it is a laxative. Does natural water that's saturated with calcium sulfate as a result of passing through soil containing gypsum meet these standards? I guess we would have to look up the KSP value for, well, no, for gypsum, you can just use the KSP value for calcium sulfate. You don't have to look up calcium sulfate dihydrate. The waters that are attached to it, they're not going to affect the KSP. And what is the concentration of sulfate in such water? Okay, so yeah, you can just look up the KSP for calcium sulfate, calculate the sulfate concentration, and compare it to the 2.6 times 10 to the negative 3 molar figure. If it's above that, then it's not safe. If it's below that, then it's considered safe. Okay, moving on. Number 10, not number 10, problem slide 10. Or is it problem slide 11? Looks like the 11th one, but anyway. 24, perform the following calculations. Silver ion concentration in a saturated aqueous solution of silver bromide. And what will it be when enough potassium bromide has been added to make the bromide concentration 0.050 molar? Okay, let's do this one. It's pretty simple, but let's do it. Okay, so silver bromide is 5.0 times 10 to the negative 3. So So that's for silver bromide. Wait, 3? No, that can't be right. 13. 5.0 times 10 to the negative 13. I don't know how I got 3. Okay, so normally, if you just dunk silver bromide in pure water, you're going to get KSP equals S squared, square root of 5.0 times 10 to the negative 13 is about 7.1 times 10 to the negative 7. So that's for part A, 7.1 times 10 to the negative 7. Part B says, what will the silver concentration be if enough potassium bromide has been added to make the bromide concentration 0.050? Really simple stuff. Plug in 0.05 here, divide it over to the other side, and you're good to go. 5.0 over 0.05, that's 100. So that's 1.0 times 10 to the negative 11. Whoops. 1.0 times 10 to the negative 11. All you have to do is plug in the bromide concentration and divide it over. And I guess I should state that those are in units of molarity. In part C, what will the bromide concentration be when enough silver nitrate has been added to make the silver ion concentration 0.020 molar? Okay, in that case, bromide concentration is KSP divided by 0.020, which effectively is multiplying it by 50. So that's times 5 is 25, and then that's 250, or 2.5 times 10 to the negative 11. I think I did that right. Let's see. 250. Yeah. Okay. There we go. Pretty simple. What else do we have here? 25. The solubility product of calcium sulfate dihydrate is 2.4 times 10 to the negative 5. What mass of this salt will dissolve in 1 liter of 0.010 molar sulfate ion? Okay, so calculate the molar solubility in a solution that already has some sulfate ion present. And once you've got that molar solubility, multiply it by the number of liters, which in this case is just 1 liter, and that'll give you the number of moles, and then multiply by the molar mass of your calcium sulfate dihydrate, and you've got the mass that will dissolve. You know how to do that, so I'll leave it up to you. 26. Assuming no equilibria other than dissolution are involved, calculate the concentrations of ions in a saturated solution. We already saw something like this. 27. Same. 28. The following concentrations are found in mixtures of ions in equilibrium with slightly soluble solids. From the concentrations given, calculate KSP for each of the slightly soluble solids indicated. Okay, so they give you the final concentrations, and you can calculate KSP from that. So silver bromide, just multiply them. Calcium carbonate, same thing. lead fluoride, multiply the lead by the fluoride squared. So 2.1 times 10 to the negative 3 times the square of 4.2 times 10 to the negative 3. So yeah, really you just have to be careful about the balancing coefficients and know when to square and cube things. But otherwise, it's really easy. In fact, it probably should have been one of the earlier problems. Is 29 the same? Yes, 29 looks like the same thing. Okay, what does this next set have? Which of the following precipitates from a solution that has the concentrations indicated? Ah, okay, so let's actually talk about precipitation using one of these. This is a nice way to segue into our next subtopic. So, potassium perchlorate, that's not going to have a KSP value associated with it. At least I don't think it should, because potassium is soluble with anything. B, that's... Okay, that's going to involve some complex ion stuff. We'll look at complex ions in video number 20 for those of you that are going to stick around for that long. I know not everybody needs to know about them. What about part C? Okay, part C looks like something decent and doable. So we've got lead 2 iodide. Lead 2 iodide. Where is it? Not listed in this book, then it'll probably be listed somewhere in here. Okay, lead 2 iodide, 1.4 times 10 to the negative 8. KSP equals 1 point, I forgot it already, 1 point, where'd it go? 4. 1.4 times 10 to the negative 8. Okay, so they gave us the lead concentration and the iodide concentration. Lead concentration, or lead 2 concentration, I should say, is 0.003 molar. Only 1 sig fig, but I guess this is more of a qualitative question anyway, so sig figs aren't really going to matter all that much. Iodide concentration is 1.3 times 10 to the negative 3 molar. And let's figure out where this is at. This is not necessarily at equilibrium. So let's calculate our QSP. It's going to be 0.003 times 1.3 times 10 to the negative 3 squared. I know it's squared because, well, I can write it real quick. PbI2 gives us 1 lead ion and 2 iodide ions. Okay, so multiplying that out, 0.003 times the square of 1.3 times 10 to the negative 3 is about 5.1 times 10 to the negative 9. Okay, and that is less than KSP, so in fact it's too far left. Equilibrium would be to the right of where we're currently at. So if there's any more solid lead 2 iodide present in this container, in the container that has these ions, then we will see more of it dissolve until you get up to 1.4 times 10 to the negative 8. We have too few ions, not too many. If it were the opposite, if I got something like 5.1 times 10 to the negative 7, then that would be more than KSP. That would mean equilibrium would have to shift left, and you would see precipitation. But right now you've got an unsaturated solution. Okay, and D probably plays out the same, or similarly. 31, is that the same thing? Which of the following compounds precipitates from a solution that has the concentrations indicated? Yeah, similar process. So calculate QSP, compare it to KSP. If Q is higher, then precipitation will occur. If Q is lower, you have an unsaturated solution, and if Q is equal to KSP, then you have a saturated solution. Okay, what about this next set? Calculate the concentration of thallium 1 ion when thallium chloride just begins to precipitate from a solution that is 0.0250 molar in chloride. Okay, just begins to precipitate means that Q is equal to K. So basically the same thing that we did with the silver bromide question a few minutes ago. Just take KSP divided by, I guess in this case, both of them are going to be to the first power because thallium 1 chloride gives you 1 thallium ion and 1 chloride ion. So yeah, just take the equilibrium constant, the KSP value for thallium chloride, which I think we had earlier. I don't remember where I listed it though. Oh, I think it might have been this one, 1.7 times 10 to the negative 4, and you can't see what I'm doing. I think this was the thallium chloride one. So 1.7 times 10 to the negative 4 divided by 0.0250 should give you the thallium ion concentration. Okay, 33, does that add anything new? Calculate the concentration of sulfate ion when it just begins to precipitate. Yeah, just begins to precipitate means that you do have a saturated solution. So Q is equal to K. Nothing too strange there. 34, same thing. 35, same thing. 36. Calculate the concentration of fluoride required to begin precipitation of calcium fluoride in a solution that is 0.010 molar in calcium ion. It's the same thing. Just be careful with the fluoride. Its concentration needs to be squared in your KSP expression. Let's go ahead and do it. It shouldn't be too hard. Calcium fluoride is a KSP of 3.9 times 10 to the negative 11. Equals your calcium ion, which was 0.010, times your fluoride ion squared. Okay, divide by 0.010, take the square root, done. 37, same. 38. Same. 39. Same thing. What about 40? A volume of 0.8 liters of a 2 times 10 to the negative 4 molar barium nitrate solution is added to 0.2 liters of 5 times 10 to the negative 4 molar lithium sulfate. Does barium sulfate precipitate? Explain your answer. Okay, let's work this one out. Not too different from anything we've seen. We already talked about solving for QSP and comparing it to KSP. And this is the same thing, but with a few more steps involved. So 0.8 liters at 2 times 10 to the negative 4 molar. So 0.8 liters of 2 times 10 to the negative 4 molar. I guess barium nitrate is just going to supply us with the barium ion. 1 molar of barium ion per molar of barium nitrate. And then divide that by the, so that gives you the moles of barium ions. Divide it by the new total volume. We're mixing 0.8 liters with 0.2 liters, so the total volume is going to be 1 liter in the end. So that's the new barium concentration. At least, well, it's the initial barium concentration upon mixing, and it might decrease if barium sulfate precipitates out. For lithium sulfate, we've got 0.2 liters of 5 times 10 to the negative 4. So we've got 0.2 liters of 5 times 10 to the negative 4 molar lithium sulfate, which gives us 1 molar of sulfate per molar of lithium sulfate. Divide that by the new total volume, and that's your sulfate concentration. Okay, and barium sulfate, the balancing coefficients are 1, 1, and 1, so it's just barium to the first power times sulfate to the first power. If that is greater than 1.1 times 10 to the negative 10, that's our KSP value here. KSP is 1.1 times 10 to the negative 10. So if after multiplying the barium concentration and sulfate concentration, you get a value greater than 1.1 times 10 to the negative 10, then precipitation will occur. Okay, next set. Perform these calculations for nickel 2 carbonate. With what volume of water must a precipitate containing nickel carbonate be washed to dissolve 0.100 grams of this compound? Calculate the molar solubility. Convert the grams to moles, and using the molar solubility, calculate the amount of liters needed to dissolve however many moles 0.1 grams turns out to be. Nothing too difficult there. Part B, if the nickel 2 carbonate were a contaminant in a sample of cobalt carbonate, cobalt 2 carbonate I should say, what mass of cobalt 2 carbonate would have been lost? Keep in mind that both nickel 2 carbonate and cobalt 2 carbonate dissolve in the same solution. That's a bit of a deeper question. So cobalt 2 carbonate has a lower KSP value, but it's going to give you the same balancing coefficients if you write out the equation. 1 and 1 and 1. That means that wait, what mass of cobalt 2 carbonate would have been lost? Oh, because it would be forced to precipitate out. Okay, I see. So in that case, what you would have to do is calculate the concentration of carbonate from the nickel 2 carbonate. Calculate the concentration of carbonate from the nickel 2 carbonate, and I feel like this problem needs to provide a little bit more information. I can kind of piece together what they want. I know what they're getting at. Since the nickel 2 carbonate is in there and its KSP is higher, it allows more carbonate to be present in solution than you would have in the presence of the cobalt ion. So so the fact that you have excess carbonate ion in there will force some of your cobalt 2 carbonate to precipitate out. And they're basically asking how much cobalt 2 carbonate is precipitated out. So you would get the carbonate concentration, take the KSP of cobalt 2 carbonate, and divide it by the carbonate concentration to the first power, since the balancing coefficients are all ones. And that would do it. 1.0 times 10 to the negative 12 divided by, I guess it would be the square root of 1.36 times 10 to the negative 7, because the molar solubility of nickel 2 carbonate gives KSP equals S squared. I feel like they should have given a little bit more information there, because it feels like I'm having to make assumptions here about the amount of carbonate from the nickel 2 carbonate versus the amount of carbonate from the cobalt 2 carbonate, which could be negligible. But anyway, moving on. 42, iron concentrations greater than 5.4 times 10 to the negative 6 molar in water used for laundry purposes can cause staining. What hydroxide concentration is required to reduce the iron 2 ions to this level? Okay, so we've done that. KSP divided by KSP divided by 5.4 times 10 to the negative 6 equals hydroxide squared. Take the square root. Nothing too hard. 43. We've got a solution that's 0.010 molar in both copper 2 and cadmium ions. What percentage of cadmium ion remains in the solution when 99.9% of the copper 2 ion has been precipitated as copper sulfide by adding the sulfide ion? So I guess I would have to compare the KSPs of copper sulfide and, well, copper 2 sulfide and cadmium sulfide. Let me look those up. And maybe we should talk a bit about precipitation, selective precipitation. Copper 2 sulfide, 6 times 10 to the negative... Oh, wait, that's... Let me look it up in this other chart instead. 8.5 times 10 to the negative 45. Okay, let me actually write this down. So, without the hydrolysis step, it's 8.5 times 10 to the negative 45. And then for cadmium sulfide, where is cadmium? 1.0 times 10 to the negative 28. Okay, so that's cadmium sulfide, and I'll switch to the document camera in a minute. I haven't forgotten. That's one thing I've gotten better at while recording these videos. Okay. So, if you add sulfide ion gradually and start precipitating out the copper sulfide, then, well, the sulfide ion concentration never reaches a high enough level to start precipitating out the cadmium sulfide. The KSP value for cadmium sulfide is higher, so you're not going to see it precipitate until all of the copper 2 sulfide has precipitated. And even then, if you manage to precipitate out the last copper 2 ion, then at that point you have a solution that contains no sulfide ions. So you still have to add even more sulfide ions in order to precipitate out the cadmium. Whatever its concentration is, if you multiply by a concentration of 0, then your Q value is, well, 0. So it's impossible for Q to be greater than KSP until a significant amount of additional sulfide ion has been added. Now, you can actually skip having to precipitate out all of the copper 2 ion if you dump in a lot of sulfide ion all at once, such that you have a really high concentration going in there. At that point, you would see both the copper 2 sulfide and the cadmium sulfide precipitating at the same time. One will probably precipitate more than the other, but yeah, if you just suddenly introduce a high concentration of sulfide ions, not all of them are going to be grabbed by the copper. But generally speaking, the lower KSP value is easier for QSP to exceed. It's easier to reach a situation where QSP is greater than KSP of, in this case, the copper sulfide, copper 2 sulfide. Oh, wait. So it's possible to reach this state where your reaction quotient is high enough that it exceeds the KSP of the copper 2 sulfide, but is still below the KSP of the cadmium sulfide. If that is the case, then this equilibrium will have to shift left and cause precipitation, while this is still not even at equilibrium. So that's the main thing that I want you to take away from that problem. And yeah, you can use that process to carefully separate ions out based on differing solubilities. Based on their different solubilities, it is possible to separate those ions out. What else do we have? So that was 43. 44 is similar business. Compare the KSPs of silver chloride and lead 2 chloride. What is the silver ion concentration when lead 2 chloride begins to precipitate? The same as it was in the beginning. The silver ion concentration cannot decrease at all if the lead precipitates first. Silver has to wait for lead to finish precipitating, or you just add so much chloride ion in the beginning that it starts out at a high enough concentration to precipitate both of them, and then some of the silver ions will catch some chloride ions. So very similar to 43. 45. What reagent might be used to separate the ions in each of the following mixtures, which are 0.1 molar with respect to each ion? In some cases, it may be necessary to control the pH. Hint, consider the KSP values given in the appendix. So there is actually a chart in my book. You probably don't need to memorize this, but there is a set of guidelines, a nice flow chart for separating out different ions. You can probably find this online if you go to Google Images and look up selective precipitation. You can probably find this on Google Images. But yeah, if you start with a mixture of all of these different ions, then you can, through various processes, separate them based on their solubilities. So they've put them into 5 different groups: blue, green, purple, red, and yellow. And yeah, so the first group, things that precipitate with the chloride ion, so that would be silver, mercury 1, and lead. All other chlorides are perfectly soluble, so that's how you would isolate those 3 from the rest of these other ions if they're present. And yeah, you can just follow the flow chart, and it's not too hard to understand the basic idea behind it. Again, I don't think you need to memorize this, but go through it once and try to understand it. I think that's a good mental exercise to go through. But in terms of memorization, I strongly doubt that you'll need to memorize this, no matter which version of the general chemistry course you're taking. Is that at the right angle? Doesn't feel like it. Maybe it's my papers that are angled. No, definitely not at the right angle. Is that? No, that's too far. There we go. Realigning this thing every time. It always feels like you're doing it right, but I digress. Moving on. We have... Oh, right, we just did this one. Or, well, we talked about it, kind of. So, yeah, just look at both of them and see, first of all, see if there's an ion that precipitates with one but not with the other. So, for example, if it was silver versus copper ion, I know that silver is insoluble with chloride while copper is soluble, so I would use the chloride ion to separate silver from copper. But if I can't find anything that precipitates one without the other, then the next thing I do is find an ion that has different KSP values for each of them. So if I look at, well, copper and mercury 1, so part A, I can use chloride to separate them because mercury 1 does precipitate with chloride while copper 2 ion does not. Sulfate and chloride. I guess I could use copper. Copper sulfate, I'm pretty sure. Copper 2 sulfate is insoluble. Oh, never mind. Calcium. Calcium sulfate is insoluble while calcium chloride is soluble, so I would go for calcium there. Part C, just like part A, mercury and cobalt 2, I should say mercury 1 and cobalt 2, you can use chloride or bromide or iodide to separate them. Zinc and strontium. I don't know if there's anything that dissolves one of them without the other. So the next thing I would do is look at something that precipitates both of them. So in front of me I see zinc carbonate and strontium carbonate. Their KSPs are, let's see, zinc carbonate is 1.0 times 10 to the negative 10, and strontium carbonate is 9.3 times 10 to the negative 10. Those are pretty close to each other. So if I can find something where the KSP values are further apart, that would be better. And again, the best thing is if you can find an ion that precipitates one of them without the other, but sometimes you have no choice. That's the basic idea behind problem 45. Let's take a look at this next set. A solution contains 1.0 times 10 to the negative 5 moles of potassium bromide and 0.10 moles of calcium chloride per liter. They could have just said it was 0.1 molar in potassium chloride, but okay. Oh, actually, I'm guessing the per liter refers to both the bromide and the chloride. Silver nitrate is gradually added to this solution. Which forms first, silver bromide or silver chloride? Both of them have the same balancing coefficients for their dissociation, so you can just compare the KSP values directly, and whichever one has the lower KSP will precipitate out first. 47, I'm guessing it's in the same vein. Yeah. 48, calcium ions in human blood serum are necessary for coagulation. Where's the question part of this? If normal blood serum with a buffered pH of 7.40 contains 9.5 milligrams of calcium ion per 100 milliliters of serum, what mass of potassium oxalate is required to prevent the coagulation of a 10 milliliter blood sample that is 55% serum by volume? So, in other words, how much it takes to start precipitating out the calcium ion. Okay, we've done problems like that before. It probably involves a few more additional steps for setting it up, but I think I'll pass on that one. 49, 50% of urinary calculi, also known as kidney stones, consist of calcium phosphate. The normal mid-range calcium content excreted in the urine is 0.10 grams of calcium ions per day. Says, what's the maximum concentration of phosphate ion that urine can contain before a calculus begins to form? Okay, so again, it's asking you to determine the concentration at which precipitation occurs. We've already done simpler versions of these problems. These just have a little bit more extra steps to set them up. Probably not something you'd be asked. I mean, this feels out there even for an AP free response problem. But, you know, it's something you can think about after you've mastered all the other stuff. 50, the pH of normal urine is 6.3, and the total phosphate concentration, so all the different types of phosphates, pure phosphate, hydrogen phosphate, dihydrogen phosphate, and phosphoric acid, is 0.020 molar. What is the minimum concentration of calcium necessary to induce kidney stone formation? And it refers back to exercise 49. So look up calcium phosphate, calcium hydrogen phosphate, calcium dihydrogen phosphate, and I'm not sure if there's a KSP value associated with calcium reacting with phosphoric acid, but I would just look at each of those four and find the KSP values for them, if I'm understanding this correctly. No. Okay. Just look up the KSP for calcium phosphate, and as you start precipitating out phosphate ions, some of the hydrogen phosphate will turn into more phosphate, some of the dihydrogen phosphate will turn into monohydrogen phosphate, and so on. I think that's what they mean when they total up all of those phosphate concentrations. That's because you essentially have a total of 0.020 molar of the phosphate ion, even if it's not all currently in the form of the pure phosphate ion. The point is, if you start running out of phosphate, then those other solutes will start producing phosphate. So it's the same as having 0.020 molar phosphate concentration. In which case, just like the previous two, it's KSP divided by the concentration of the other thing. Squared if it needs to be squared, cubed if it needs to be cubed, and so on. Okay. Nothing interesting happened on that page then. What about this next one? Magnesium metal is isolated from seawater by the following sequence of reactions. Seawater has a density of 1.026 grams per cubic centimeter and contains 1,272 parts per million of magnesium as magnesium ion by mass. What mass in kilograms of calcium hydroxide is required to precipitate 99.9% of the magnesium? Okay, calculate what 0.1% of the magnesium would be. Set that to your magnesium ion concentration, and then do KSP divided by the magnesium concentration equals, I'm guessing, hydroxide concentration squared take the square root, and I think that would do it. That would give you the amount of hydroxide you need. Then go backwards from there, figure out how much calcium hydroxide that is, and I think from there you can answer the rest of the problem. It's one of those challenge problems, so again, I would postpone this until you master the basics. And you can probably get by without knowing how to do this at all, but I would hope that I've taught you well enough up to this point that you can handle this. It doesn't look like anything too out there. It's just got a lot of steps involved. 52. Is that more of the same? What concentrations of lead 2 ion and iron 2 ion remain in the solution? Remember to compare the KSP values. The one with the lower KSP value is going to precipitate out first if any precipitation happens at all, and the one with the higher KSP value is not going to precipitate at all. Its concentration will stay constant until the other one completely precipitates out. And I shouldn't be saying higher or lower KSP. It's higher or lower solubility. But yeah, you know the drill with that one. We've discussed similar problems. 53, perform the calculations involving concentrations of iodate ions. Iodate ion concentration of a saturated solution of lanthanum 3 iodate was found to be 3.1 times 10 to the negative 3 molar. Find the KSP. Okay, so they're assuming there that it was just placed in pure water. So KSP equals, what will that be? 27s to the 4th. Okay, yeah, we've seen stuff like this. 54, calculate molar solubility of silver bromide and 0.035 molar sodium bromide. We've done that, or we've done stuff similar to it at least. 55. How many grams of lead hydroxide will dissolve in 500 milliliters of a 0.050 molar lead to chloride solution? Oh, okay, so there's already a little bit of lead in there, so you're going to have to calculate that, and then calculate how much additional lead can be dissolved. So, yeah, calculate the lead ion concentration from lead chloride in pure water, and then adding lead hydroxide on top of that, figure out how much lead 2 hydroxide you can actually dissolve after accounting for the lead 2 ion already being present due to the lead chloride. Once you've got the molar solubility of the lead hydroxide in lead chloride, multiply by 0.5, since that's 500 milliliters converted to liters, and that'll give you the moles. Multiply by molar mass, you get the grams. Okay. And this is the last set of problems, and after this, just a little note on solubility in strong acids or bases, and then we'll wrap things up. 57. How many grams of milk of magnesia would be soluble in 200 milliliters of water? KSP is there. Include the ionic. Okay, we've done this before. So magnesium hydroxide in pure water, get the molar solubility. Multiply by the volume, get the moles. Multiply by the molar mass, get the grams. 58. Two hypothetical salts, LM2 and LQ, have the same molar solubility in water. If KSP for LM2 is 3.20 times 10 to the negative 5, what is the KSP for LQ? Ooh, not hard, but interesting. Let's do that one. So they both have the same molar solubility. One of them is LM2, which will give us this. And the other one is LQ. So they both have the same molar solubility S. So for this one, KSP is going to be 4s cubed. 4s cubed equals 3.20 times 10 to the negative 5 is what they said. 3.20 times 10 to the negative 5. Okay, so that's the KSP for this. And the KSP for this is going to just be S squared equals, well, it's equal to 4s cubed divided by 4s. I'm overthinking this. Solve this for s and plug it in there. I was hoping for something mathematically profound to drop out of it, but that might be overdoing it. 59. The carbonate ion concentration is gradually increased in a solution containing divalent cations of magnesium, calcium, strontium, barium, and manganese. Which of the following carbonates will form first? Which of the following will form last? Explain. Okay, so magnesium carbonate gives you one magnesium, one carbonate. Calcium carbonate, same thing. Strontium carbonate, 1 to 1. Barium carbonate and manganese 2 carbonate. All of those give you 1 to 1, same balancing coefficients. So start from the lowest KSP, that will precipitate out first. And once it's gone, the next lowest starts precipitating until it's gone, then the next lowest, then the next lowest, until you've precipitated all of them out. And number 60, how many grams of zinc cyanide would be soluble in 100 milliliters of water? Include the balanced reaction and the expression for KSP. We've done this. Get the molar solubility, multiply by the volume, get the moles, multiply by the molar mass, get the grams. All right, then I guess that's it for problems. There's one last little thing that we need to talk about, and that is the concept of amphoterism. So in front of you, you see a set of equations involving complex ions formed by aluminum. It turns out that aluminum, its solubility increases in both acidic and basic solutions. This is what we call an amphoteric compound, similar to the word amphiprotic, but not quite the same. So there's not really that much to say about it right now because we haven't talked about complex ions. We're saving that for video number 20. But the formation of complex ions does allow you to dissolve things that you otherwise couldn't dissolve. For example, silver chloride is normally not soluble in pure water, not that soluble anyway. But you can significantly increase the solubility of the silver ion if you add lots of ammonia to the solution, because the ammonia will interact with the silver in such a way that it forms the following complex ion. Silver ion, well, if you have something like silver chloride and you react it with ammonia in solution, then you can get this complex ion that is basically a silver ion with two ammonia molecules. I guess the word would be coordinate bonded to it, having an overall charge of +1, and of course you'd have the chloride ion floating out there alone. So yeah, silver chloride much more soluble in a basic solution of ammonia. So substances that increase in solubility, whether you put them in a basic solution or an acidic solution, those are called amphoteric substances. Their solubility increases under acidic conditions or under basic conditions. And yeah, the aluminum complexes are examples of that. It's just really something you need to know about. Amphoteric versus amphiprotic. So which is the bigger category? All amphiprotic substances are amphoteric, but not all amphoteric substances are amphiprotic. I can say that the aluminum ion is amphoteric, but it's not amphiprotic because, well, it can't provide protons. It doesn't have any protons included. So just on the basis of that alone, you can tell that aluminum is not amphiprotic. So amphiprotic is the smaller category. And I think that's pretty much everything I wanted to cover. I feel like I'm forgetting something, but it's probably... Let me check with my notes. Well, I covered everything that's listed on my notes, so I think we're good to go. But if I have forgotten anything, then I'll probably mention it in a pinned comment, and if it's too complicated for a comment, then I will talk about it in the next video. Otherwise, the next video is going to make use of all the equilibrium we've learned and tie it back into energy. We're going to bring back our delta H. I hope you remember how to calculate standard enthalpies of formation and whatnot, because we're going to be introducing two new similar concepts, free energy and entropy, which work in kind of the same way. But yeah, that's the next chapter, thermodynamics. That's what we'll be covering next. Then it's off to electrochemistry, then nuclear chemistry, then organic chemistry, and then the chemistry of coordination compounds, and then this series will be done. It'll probably total like 100 hours of recording. So I'll see you in the thermodynamics video. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you in the next video.